Have you ever stopped to wonder what consciousness really is, or why the smallest particles in our universe, like electrons and photons, behave so strangely, defying the rules of everyday life? For centuries, these two mysteries, the nature of the mind and the nature of matter, have been pursued along separate, parallel tracks. But what if these tracks are not parallel at all? What if they are destined to converge? A bold and speculative idea, known as the theory of quantum consciousness, suggests that these two great mysteries might be two sides of the same deep coin. It proposes that our minds, the very seat of our subjective experience, could operate on the same mind-bending principles that govern the bizarre and beautiful world of the quantum realm. In quantum mechanics, as we have seen, particles can exist in a superposition of multiple states at once, a ghostly blend of possibilities. They can be instantaneously connected across vast cosmic distances through the spooky phenomenon of entanglement, and their very reality seems to be shaped by the act of observation. Could our minds work in a similar way? Could our thoughts and ideas exist as a superposition of unformed potentials, only crystallizing into a definite concept when we focus our attention? Could our feelings of connection, of empathy, of intuition be a macroscopic echo of quantum entanglement? And could consciousness itself be the ultimate observer, the mysterious agent that collapses the wave function of possibility into the definite, classical reality we experience? This is a breathtaking idea, one that challenges our most fundamental assumptions about both the physical world and our own inner selves. It is a journey to the very edge of science, a place where physics, neuroscience, and philosophy meet, a place where the mysteries of the cosmos and the mysteries of the mind might just be one and the same. In our everyday classical world, the act of observation is a passive one. When we look at a cup of coffee on a table, we assume that our gaze does not affect the cup's properties. The cup is there. It has a definite position, a definite temperature, whether we are looking at it or not. But in the quantum world, the rules are different. Here, the simple, seemingly innocent act of observing a particle can fundamentally change its behavior. This is the observer effect, one of the most puzzling and profound phenomena in all of science. But what precisely does it mean? It is not simply that our measuring devices are clumsy and inevitably disturb the delicate quantum systems they are trying to measure, though that is certainly part of the story. To see an electron, for example, we have to bounce a photon of light off of it. This photon carries energy and momentum, and in the act of a collision, it will inevitably give the electron a kick, changing its state. It is like trying to determine the precise position of a billiard ball by hitting it with another billiard ball. The very act of measurement changes the thing you are trying to measure. But the observer effect in quantum mechanics is deeper and stranger than this. It is not just about a physical disturbance. It is about the role of information and the nature of reality itself. It is intimately tied to the concept of the collapse of the wave function. In the quantum world, before a measurement is made, a particle is described by a wave function, a mathematical object that represents a superposition of all its possible states. An electron does not have a single position. It is a cloud of probability. The moment we make a measurement, the moment we gain information about its position, this wave function is said to collapse. The cloud of possibility vanishes, and the electron is found at a single, definite location. Why does this happen? Why does the act of observation force the universe to abandon its ghostly, probabilistic nature and choose a single, classical reality? This is the heart of the quantum measurement problem, and it is a mystery that has no universally accepted answer. One of the oldest and most influential attempts to address it is the Copenhagen interpretation. developed by the founding fathers of quantum mechanics, Niels Bohr and Werner Heisenberg. In this view, there is a fundamental distinction between the quantum world of microscopic systems and the classical world of our macroscopic measuring devices. Quantum systems do not have definite properties until they are measured. The act of measurement is what brings these properties into being. An electron does not have a position until we measure it. This is a pragmatic and somewhat instrumentalist view. It provides a set of rules that work incredibly well for making predictions, but it does not offer a deep ontological explanation for why the rules are the way they are. It leaves the process of measurement as a kind of black box, a mysterious and unexplained, shifty split between the quantum and the classical. The philosophical unease created by the Copenhagen interpretation, with its seemingly arbitrary division of the world and its central, unexplained role for the observer, has led to a host of alternative interpretations, each offering a different, and often equally bizarre, picture of reality. The most famous of these is the many worlds interpretation, first proposed by the physicist Hugh Everett III in a bold and elegant move. Everett suggested that the collapse of the wave function never happens. The wave function and its smooth, continuous evolution according to the Schrödinger equation is the whole story. When a measurement is made, the universe does not choose one outcome. Instead, all possible outcomes are realized, each in its own, separate, parallel universe. The universe itself splits or branches into a multitude of realities. In one universe, the electron is found at position A. In another, it is found at position B. The observer also splits, with one version of you experiencing outcome A and another version experiencing outcome B. In this view, Schrödinger's cat is never in a superposition of alive and dead. There are simply two separate universes, one in which the cat is alive, and one in which it is dead. This is a breathtakingly grand and economical vision. It does away with the mysterious collapse and the special status of the observer, and it restores a kind of deterministic, universal reality. But it does so at the price of postulating an unobservable and possibly infinite number of parallel worlds. At the other end of the interpretational spectrum lies a class of theories that seek to restore a more classical, intuitive picture of reality. The pilot wave theory, first conceived by Louis de Broglie and later rediscovered and developed by David Bohm, proposes that quantum particles are, in fact, classical-like particles. They always have a definite position, even when we are not looking. The wave function is not just a description of probabilities. It is a real, physical pilot wave that guides the motion of the particle. The particle is like a surfer riding on the surface of this underlying, invisible wave. In this picture, the apparent randomness of quantum mechanics is not fundamental, but is a result of our ignorance of the particle's precise initial position and the complex non-local nature of the pilot wave. This is a fully deterministic theory that reproduces all the statistical predictions of standard quantum mechanics. But it does so by introducing a new, unobservable entity, the pilot wave, and by embracing a deep and spooky non-locality, where the motion of a particle here can be instantaneously influenced by the state of the entire universe. And then there are the objective collapse theories, which propose that the collapse of the wave function is a real physical process that happens spontaneously, without the need for an observer. The collapse is a random, probabilistic event, and its likelihood depends on the size and complexity of the system. For a single, isolated particle, the chance of a spontaneous collapse is infinitesimally small, so it can maintain its superpositional nature for a long time. But for a macroscopic object like a cat, which is made of trillions of entangled particles, the probability of a collapse occurring in one of its constituent particles becomes overwhelmingly high, triggering a rapid chain reaction collapse of the entire system. This elegantly explains why we never see macroscopic superpositions, but it does so by modifying the fundamental Schrödinger equation and introducing new, and as yet unobserved, physical parameters. The ongoing debate between these different interpretations highlights the profound and still unresolved conceptual crisis at the heart of modern physics. We have a mathematical formalism that works with stunning, unprecedented accuracy, but we have no consensus on what it is telling us about the nature of reality. Is the universe fundamentally probabilistic or deterministic? Is reality created by observation, or does it exist independently of us? Is there one world, or are there many? And what, if any, is the role of consciousness in this cosmic drama? These are questions that may not have a final scientific answer, but they are questions that force us to confront the limits of our own understanding and to stand in a state of profound and humble awe before the deep, beautiful, and endlessly fascinating mystery of the quantum world. The principle of superposition, the idea that a quantum particle can exist in a multiplicity of states at once, is not just a strange feature of the subatomic world. It is a powerful lens through which we can view the nature of our own consciousness. While the idea of a quantum mind is highly speculative and on the very fringes of mainstream science, the metaphorical resonance between the quantum world and our own inner experience is undeniably profound and thought-provoking. Consider the nature of a thought. Before a thought becomes a clear, definite, and articulated concept, it often exists as a vague, fuzzy, and unformed potential. It is a superposition of different possible meanings, different emotional colorings, different associative connections. It is only through the act of focusing our attention, of measuring our own mental state, that this superposition collapses into a single, definite thought. The creative process is a particularly clear example of this. An artist, a writer, a musician, often speaks of being in a state of flow, a state where they are open to a vast field of possibilities, a state where ideas seem to emerge spontaneously, without conscious effort. This is a state of mental superposition, a state where the mind is not locked into a single, linear track of thought, but is free to explore the vast, interconnected web of the unconscious. The aha moment, the flash of insight that solves a difficult problem, is the experience of a new and previously unconsidered possibility collapsing into a definite reality. It is a moment of creative quantum leap. The experience of making a decision is another powerful parallel. Before we make a significant choice, we often feel torn between different options. We can see the merits of each path. We can imagine the different futures that each choice would lead to. We are, in a very real sense, in a superposition of all these potential futures. The act of making the decision, of committing to one path, is the act of collapsing this superposition. It is a creative, world-shaping act that transforms the potential into the actual. This is why decisions can be so difficult and so anxiety-provoking. It is the existential weight of collapsing a whole universe of possibilities into a single, irreversible reality. But the most universal and profound experience of mental superposition is the one we all enter every night, the state of sleep and dreaming. As we drift off to sleep, the collapsed, classical self of our waking life begins to decohere. The rigid boundaries of the ego dissolve, and we are immersed in the fluid, multi-layered, and superpositional world of the unconscious. In our dreams, we are not a single, coherent identity. We can be a child and an old person at the same time. We can be both the pursuer and the pursued. We can feel both terror and exhilaration simultaneously. The normal rules of logic, of time, of identity are suspended. The dream is the psyche's nightly return to its own native quantum state, a state of pure, uncollapsed potential. This is not to say that the brain is a literal quantum computer, or that our thoughts are actual quantum states. The brain is a warm, wet, and noisy biological system. an environment that is generally thought to be far too disruptive for the delicate, coherent states of the quantum world to survive for any significant amount of time. The challenges of decoherence are immense, and yet the metaphorical parallel is too strong to ignore. The language of quantum mechanics of superposition, of potential, of collapse, of interconnectedness provides us with a new and remarkably rich vocabulary for describing the deep and often paradoxical nature of our own subjective experience. It invites us to see our minds not as simple, classical machines, but as complex, dynamic, and endlessly creative quantum-like systems. It suggests that the strangeness of the quantum world is not something that is out there in the abstract realm of particles and fields. It is something that is in here, in the very fabric of our own conscious awareness. And by exploring the mysteries of the quantum world, we may, in the end, be exploring the deepest and most profound mysteries of ourselves. The phenomenon of quantum entanglement, the spooky action at a distance that so perplexed Einstein, is a direct and powerful testament to the non-local and holistic nature of the universe. It tells us that our classical intuition of a world made up of separate, independent objects is a profound illusion. At a fundamental level, the universe is not a collection of things, it is a network of relationships, a single, indivisible whole. When two particles become entangled, they are no longer two separate entities. They are two aspects of a single, unified quantum state, described by a single wave function. The measurement of one particle is not an action on a separate object. It is a measurement of the entire entangled system, an act that instantaneously collapses the wave function of the whole, no matter how far apart its constituent parts may be. This is a concept that is so counterintuitive that it has taken decades of increasingly sophisticated experiments, like the Bell tests, to convince the scientific community of its reality. But the evidence is now overwhelming. The universe is, in some deep and mysterious way, non-local. This has profound implications that ripple out from the world of physics into the realms of philosophy, spirituality, and our own personal experience. If the universe is fundamentally interconnected, then the sense of separation we feel as individual beings is not the ultimate truth. We are not isolated, skin-encapsulated egos, adrift in a cold, indifferent cosmos. We are, in a very real physical sense, entangled with each other, with the planet, and with the entire history of the universe. The atoms in our bodies are the recycled stardust of ancient, long-dead stars. The information in our DNA is a 4-billion-year-old story that connects us to the very first life on Earth. We are not just in the universe, we are the universe, experiencing itself. This sense of interconnectedness is not just an abstract philosophical idea. It is an experience that we can all have, an experience that is often most accessible in states of consciousness where the dominance of the ego is relaxed, in moments of deep love, of profound empathy, of awe in the face of natural beauty. Our sense of a separate self can dissolve, and we can feel a deep and powerful sense of unity with the person, the place, or the moment we are experiencing. These are moments of conscious entanglement, moments when we touch the underlying, holistic reality of our own being. Sleep, and particularly the dream state, is a nightly immersion in this entangled reality. As the boundaries of the self become porous, our consciousness is free to roam the vast, non-local network of the unconscious. In our dreams, we can connect with people and places that are distant in space and time. We can have vivid, emotionally resonant encounters with loved ones who are far away, or even with those who have passed on. We can experience a deep sense of participation mystique, a feeling of merging with the archetypal energies of the collective unconscious. These are not just random neurological firings. They are the psyche's way of exploring its own vast, entangled web of relationships. They are a reminder that our connections to others are not severed by physical distance or even by death. The information, the emotional resonance, the shared history persists in the non-local field of our own, and the collective consciousness. The practical applications of entanglement in the realms of quantum computing, quantum cryptographies, and quantum teleportation are already beginning to transform our technological landscape. A quantum internet based on the transmission of entangled states could one day provide a form of communication that is fundamentally secure, as any attempt to eavesdrop on the communication would instantly break the entanglement and be detected. Quantum teleportation, while not the beam-me-up biscotti of science fiction, allows for the perfect transmission of the quantum state of a particle from one location to another, a technology that could be the backbone of future quantum networks. But the true revolution of entanglement may be a philosophical one. It is a concept that is forcing us to abandon our old mechanistic and fragmented worldview and to embrace a new, holistic, and interconnected vision of reality. It is the scientific confirmation of the ancient spiritual insight that we are all one. And every night, as we surrender to the mystery of sleep, we are given the chance to experience this profound truth directly, to remember our deep and beautiful entanglement with the entire cosmic web of existence. The quantum vacuum, the so-called empty space that fills the universe, is not a void of nothingness, but a plenum of potential, a seething, energetic sea from which the entire manifest world arises. This is the realm of virtual particles, a concept that is as central to modern physics as it is challenging to our classical intuition. Virtual particles are not real particles in the sense that we can put them in a detector and measure their properties. They are fleeting, transient fluctuations of the quantum fields, phantom entities that borrow a tiny amount of energy from the vacuum to pop into existence for an immeasurably short time, only to annihilate each other and disappear back into the void. Their existence is a direct consequence of the energy-time uncertainty principle. For a very brief moment, the law of conservation of energy can be violated, as long as the energy debt is quickly repaid. The quantum vacuum is a cosmic loan shark, constantly lending out and recalling these tiny packets of existence. But these are not just a mathematical fiction, a computational convenience used by physicists to make their equations work. Virtual particles have real, measurable, and profound effects on the world. We have already seen how they are responsible for the Casimir effect, the strange, attractive force between two plates in a vacuum. They are also responsible for some of the most precise and well-tested predictions of quantum electrodynamics, the quantum theory of light and matter. The magnetic moment of an electron, for example, is not a simple, fixed value. It is slightly, but measurably, different from the value predicted by the simplest form of the theory. This tiny discrepancy, known as the anomalous magnetic moment, is perfectly explained by accounting for the electron's interaction with the cloud of virtual photons and electron-positron pairs that are constantly bubbling around it. The agreement between the theoretical calculation and the experimental measurement of this value is one of the most stunning triumphs in the history of science. A testament to the very real existence of this seemingly ghostly virtual world. The concept of virtual particles also provides a new and powerful way to understand the nature of the fundamental forces. In quantum field theory, all forces are mediated by the exchange of virtual particles. The electromagnetic force between two charged particles is the result of them exchanging virtual photons. The strong nuclear force that binds quarks together inside protons and neutrons is mediated by the exchange of virtual gluons. The weak nuclear force, responsible for radioactive decay, is carried by virtual W and Z bosons. The seemingly solid and continuous forces of our macroscopic world are, at a fundamental level, a grainy, pixelated, and probabilistic exchange of these transient quantum messengers. This has profound implications for our understanding of reality. It suggests that the distinction between matter and force, between substance and interaction, is not as clear as we once thought. They are both different manifestations of the same underlying quantum fields, but the role of virtual particles extends even to the grandest cosmological scales. The phenomenon of Hawking radiation, the faint, thermal glow that is predicted to be emitted by black holes, is a direct consequence of virtual particle creation at the event horizon. A virtual particle-antiparticle pair can be created right at the edge of the black hole. If one particle falls in and the other escapes, the escaping particle can no longer annihilate with its partner. It becomes a real particle, carrying away a tiny amount of the black hole's mass energy. This process, over immense timescales, causes the black hole to slowly evaporate. It is a beautiful and profound example of how the subtle, quantum fluctuations of the vacuum can have a dramatic and tangible effect on the most massive and powerful objects in the cosmos. The world of virtual particles is a world that is forever hidden from our direct view, a world that exists on the very edge of being and non-being. But it is a world whose influence is everywhere, from the precise properties of a single electron to the ultimate fate of a giant black hole. It is the invisible, energetic, and endlessly creative engine that drives the quantum universe. The ability of a quantum particle to tunnel through a barrier that it classically should not have the energy to overcome is one of the most striking and non-intuitive predictions of quantum mechanics. It is a phenomenon that relies on the wave-like nature of particles and the probabilistic heart of the quantum world. A particle's wave function does not stop abruptly at a barrier. It decays exponentially into it. If the barrier is thin enough, there is a small but non-zeroed probability that the wave function will still have some amplitude on the other side, meaning there is a finite chance of finding the particle there. This is not just a theoretical curiosity. It is a process that is essential to life, the universe, and everything. The sun shines because of quantum tunneling. The core of the sun is a furnace of nuclear fusion, where hydrogen nuclei are fused together to form helium, releasing a tremendous amount of energy. But the temperature and pressure in the sun's core, while immense, are not quite high enough for these positively charged nuclei to overcome their mutual electrostatic repulsion and get close enough to fuse in a classical way. It is only because of the magic of quantum tunneling that they can bypass this energy barrier and initiate the fusion reactions that power our star and make life on Earth possible. Without quantum tunneling, the stars would not shine, and the universe would be a cold, dark, and lifeless place. Quantum tunneling is also the principle behind the technology of the scanning tunneling microscope, a device that has allowed us to see individual atoms for the first time. The STM works by bringing a razor-sharp metal tip incredibly close to a conducting surface. A tiny voltage is applied, and because of quantum tunneling, a small current of electrons can tunnel across the vacuum gap between the tip and the surface. This tunneling current is exquisitely sensitive to the distance between the tip and the surface, by scanning the tip across the surface and keeping the tunneling current constant. A computer can build up a three-dimensional atomic resolution map of the surface. This technology has revolutionized the fields of materials, science, chemistry, and biology, allowing us to see and manipulate matter at its most fundamental level. But the implications of quantum tunneling extend even further, into the realm of our own modern digital technology. The flash memory that is used in our computers, smartphones, and USB drives works by storing electrons in a floating gate, a tiny island of conducting material that is surrounded by a thin insulating barrier. To write information, a voltage is applied that allows electrons to tunnel through this barrier and become trapped in the floating gate. To erase the information, the voltage is reversed, and the electrons tunnel back out. Every time you save a file or take a picture with your phone, you are relying on the strange, probabilistic, and deeply non-classical phenomenon of quantum tunneling. But perhaps the most profound and speculative application of quantum tunneling is in the origin of the universe itself. As we have seen, some cosmological models propose that our entire universe may have been born from a quantum tunneling event, a spontaneous transition from a state of nothing to a state of something. This is the ultimate act of tunneling, a leap not through a physical barrier, but through the metaphysical barrier between non-existence and existence. Quantum tunneling is a beautiful and powerful reminder that the universe is not a deterministic machine, but a world of probability and potential. It tells us that barriers are not always absolute, that the impossible can sometimes happen, and that even in the face of insurmountable odds, there is always a chance, however small, of a breakthrough. It is a principle of hope, of transformation, of creative surprise, a principle that is written into the very fabric of our quantum reality. The Heisenberg uncertainty principle is not just a statement about the limits of our measurement capabilities. It is a deep and fundamental principle that reveals the inherent, irreducible fuzziness of the quantum world. It is the universe's way of ensuring that reality is never static, never fixed, and never completely knowable. The trade-off between position and momentum is the classic example, but the principle applies to other pairs of conjugate variables as well, such as energy and time. The more precisely you know the energy of a quantum system, the less precisely you can know the duration over which that energy is defined, and vice versa. This energy-time uncertainty is the principle that allows for the existence of virtual particles, the fleeting fluctuations of the quantum vacuum. It is the source of the universe's zero-point energy, the irreducible quantum jiggle that prevents anything from ever being truly at rest. It is a principle that replaces the classical world of certainty with a world of probability, a world where the future is not predetermined, but is a landscape of open potential. This has profound philosophical implications. It suggests that the universe, at its core, is not a clockwork machine, but a creative, spontaneous, and endlessly unfolding process. The inherent uncertainty of the quantum world is not a flaw. It is the very source of its novelty, its capacity for the emergence of new and unexpected forms. This resonates deeply with our own subjective experience of being. We are not deterministic automatons, our lives unfolding along a pre-written script. We are beings of choice, of creativity, of potential. We live in a constant state of uncertainty, and it is this very uncertainty that gives our lives meaning, that makes our choices matter. If the future were completely determined, there would be no freedom, no responsibility, no art, no love. The uncertainty principle is the physical guarantee of our own human freedom. It is the universe's way of saying, I have not yet decided. And this sense of openness, of potential, is an experience that is most accessible to us in the quiet, liminal state of our own minds, as we relax our focused, goal-oriented, and certainty-seeking waking consciousness, as we drift into the gentle, associative flow of daydreams or the deep, symbolic world of our sleep. We are entering a realm that is governed by a logic that is more akin to the quantum world. It is a realm where the rigid boundaries between self and other, between past and future, between reality and imagination, become fluid and permeable. It is a realm where new connections can be made, where old patterns can be broken, where new insights can spontaneously emerge. This is the creative power of the unconscious, the mind's own innate capacity for navigating the landscape of uncertainty. The uncertainty principle is not a statement of our ignorance. It is a statement about the nature of reality. It is a celebration of the possible, a testament to the fact that the universe is not a closed, finished system, but an open, creative, and endlessly surprising adventure. And we, as conscious, questioning, and dreaming beings, are privileged to be a part of that adventure. The Copenhagen interpretation, for all its pragmatic success, leaves a deep sense of philosophical unease. Its insistence on a fundamental and unexplained, split between the quantum and classical worlds, and its elevation of the act of measurement to a special collapse-inducing status, seems to many physicists to be an incomplete and unsatisfying picture of reality. This has led to a century-long search for alternative interpretations, each attempting to provide a more coherent and ontologically complete story of the quantum world. The many worlds interpretation, with its breathtaking vision of a constantly branching multiverse, offers a radically different perspective. It eliminates the mystery of the collapse by simply denying that it ever happens. The wave function is the whole story, and its smooth, deterministic evolution is the only law. This is a picture of immense elegance and simplicity, but it comes at the cost of a bloated and unobservable ontology. We are asked to believe in the existence of an infinite number of parallel universes, universes that are, by their very nature, completely inaccessible to us. Is this a price worth paying for theoretical consistency? The pilot wave theory of de Broglie and Bohm offers another path. It restores a kind of classical realism and determinism to the quantum world. But it does so by introducing a new, unobservable entity, the pilot wave, and by embracing a deep and spooky non-locality that seems to be in tension with the spirit, if not the letter, of Einstein's relativity. It is a vision of a hidden clockwork universe, a universe where the apparent randomness is just an illusion of our own ignorance. And then there are the objective collapse theories, which seek to make the collapse a real physical and universal process, independent of any observer. These theories modify the fundamental Schrödinger equation, adding new, nonlinear, and stochastic terms that cause the wave function to spontaneously collapse. This is a scientifically respectable approach, as it makes new, testable predictions. A spontaneous collapse process should, for example, produce a tiny, but constant, amount of heat, a spontaneous heating of the universe that could, in principle, be detected. So far, no such effect has been found, which places tight constraints on these models. But the search continues. The ongoing debate between these different interpretations is not just a technical squabble among physicists. It is a debate about the very nature of reality, about the relationship between the mind and the world, between the potential and the actual, between the one and the many. It is a debate that touches on some of the deepest and most enduring questions of philosophy. And it is a debate that is unlikely to be settled by a single killer experiment. It is more likely that our understanding will evolve through a slow, cumulative process of theoretical refinement and experimental constraint. A process that may lead us not to a single, final correct interpretation, but to a new, and perhaps more profound, synthesis that transcends our current, limited categories of thought. The strangeness of the quantum world is not a problem to be solved. It is a reality to be understood. And in grappling with its mysteries, we are not just doing physics. We are engaged in a deep and deeply human act of philosophical inquiry, a quest to understand our own strange, and beautiful place in a universe that is far more mysterious, more interconnected, and more full of possibility than our classical intuition could ever have imagined. The quantum world is not just a realm of strange and counterintuitive phenomena, it is also the engine of our modern technological world. The principles of quantum mechanics. Once the esoteric domain of a handful of theoretical physicists, are now at the heart of some of our most advanced and transformative technologies. Quantum computing is perhaps the most famous and most ambitious of these. By harnessing the principles of superposition and entanglement, quantum computers have the potential to solve certain classes of problems, like factoring large numbers, simulating complex quantum systems, and searching vast databases at speeds that are exponentially faster than any classical computer. This could revolutionize fields as diverse as medicine, materials science, finance, and artificial intelligence. A quantum computer could simulate the behavior of a new drug molecule with perfect accuracy, allowing for the design of more effective and personalized medicines. It could discover new materials with exotic properties, like room temperature superconductors. It could break the encryption codes that currently protect our global financial and communication systems, a prospect that is driving the parallel development of quantum-safe cryptography. But building a large-scale, fault-tolerant quantum computer is an immense scientific and engineering challenge. The quantum states of the qubits are incredibly fragile and are easily disturbed by their environment, a process known as decoherence. Protecting these delicate quantum states from the noise of the outside world is the central challenge in the field. And it is a challenge that requires a deep and practical understanding of the very quantum phenomena we have been discussing. Quantum cryptography offers a more near-term and equally revolutionary application of quantum principles. By using the properties of single photons or entangled particle pairs to encode and transmit information, it is possible to create a communication channel that is fundamentally secure. The laws of quantum mechanics themselves guarantee its security. The uncertainty principle dictates that any attempt by an eavesdropper to measure the quantum state of the photons will inevitably disturb them, and this disturbance can be detected by the legitimate users. Entanglement-based systems offer an even more robust security, as the non-local correlations between the entangled particles can be used to verify the integrity of the communication channel. These quantum communication networks are already being built and tested, and they will likely form the backbone of a future, ultra-secure quantum internet. Quantum sensors are another area where quantum mechanics is having a profound impact. By exploiting the exquisite sensitivity of quantum systems to their environment, it is possible to build sensors of unprecedented precision. Atomic clocks, which use the regular quantum oscillations of atoms as their timekeeping element, are the most accurate timekeepers ever built. They are the heart of our global positioning system, and they are being used to test the predictions of general relativity with incredible accuracy. Quantum magnetometers, based on the spin of nitrogen vacancy centers in diamond, can detect magnetic fields that are 1 billion times weaker than the Earth's magnetic field, with applications in medical imaging and materials science. And gravitational wave detectors like LIGO use quantum optics and squeezed light to measure the tiny subatomic scale ripples in space-time caused by the collision of distant black holes. Even the realm of biology is not immune to the quantum revolution. The emerging field of quantum biology is exploring the possibility that some fundamental life processes, like photosynthesis, avian navigation, and the sense of smell, may rely on quantum effects to function. The high efficiency of energy transfer in photosynthesis, for example, may be due to a process of quantum coherence, where the energy explores multiple pathways simultaneously to find the most efficient route. These are still controversial and developing ideas, but they hint at a deep and beautiful connection between the fundamental laws of physics and the emergent complexity of life itself. The quantum revolution is not just a revolution in our understanding of the universe. It is a revolution that is already beginning to reshape our world, to give us new tools, new technologies, and new ways of interacting with reality. It is a testament to the fact that the strangest, most counterintuitive, and most philosophically profound aspects of nature are also, very often, the most powerful and the most useful. The wave-particle duality, the central and most enduring paradox of the quantum world, is a profound statement about the nature of reality. It tells us that our classical categories of thought, our neat and tidy divisions of the world into things and processes, into matter and waves, are inadequate to describe the fundamental nature of existence. The universe, at its core, is not either-or, it is both and. An electron is not a particle that sometimes pretends to be a wave, nor is it a wave that sometimes masquerades as a particle. It is a quantum, a single, unified entity whose particle-like or wave-like aspect is revealed only in the context of a specific interaction, a specific measurement. This is Niels Bohr's principle of complementarity, a philosophical insight that is as deep as it is beautiful. The wave and the particle are two, complementary, and mutually exclusive faces of a single, underlying reality. You cannot see both faces at the same time, but you need both to have a complete picture. This is a paradox that is not meant to be solved, but to be held, to be contemplated, to be lived. And we do live it every day in the rhythm of our own consciousness. Our waking life is the particle aspect of our being. We are localized in space and time. We have a definite identity. We interact with the world as separate, discrete objects. Our thinking is linear, logical, and causal. But our sleeping life, and especially our dreams, is the wave aspect of our being. Our sense of a localized, separate self dissolves. We become a fluid, non-local field of awareness. Our thinking is associative, symbolic, and timeless. The rigid boundaries of the waking world give way to a reality that is interconnected, multiplicitous, and paradoxical. The double-slit experiment, with its strange and beautiful logic, is not just a demonstration of the duality of a single electron, it is a mirror of the duality of our own being. When we are observed by the demands of the external, social world, we collapse into a single, particle-like identity. We choose a path, we play a role. But when we are unobserved in the quiet, inner space of our own minds, in the solitude of our sleep, we are free to explore the full, wave-like potential of who we are. We can be all things at once. We can pass through all the slits of our own possibility. The wave-particle duality is not a flaw in our understanding. It is a deep, structural feature of reality itself. It is the creative tension between the one and the many, between the definite and the potential, between the collapsed world of our waking lives and the uncollapsed, superpositional sea of our dreams. To embrace this duality is to embrace the fullness of our own human experience. It is to recognize that we are both the finite, mortal beings who walk the earth, and the infinite, timeless waves of consciousness that dream the cosmos into being. The quantum vacuum, with its incessant, energetic hum of zero-point energy, is not just a strange and abstract concept of theoretical physics. It is the very womb of reality, the generative source from which all of existence arises. The idea that space, the seemingly empty void between the stars, is actually a seething, vibrant ocean of potential is a profound and revolutionary one. It tells us that the universe is not a static, finished creation, but a dynamic, ongoing process of emergence. This has a powerful and beautiful resonance with our own inner experience, the silent, empty spaces of our own consciousness, the moments of quiet contemplation, the pauses between thoughts. The deep, restorative emptiness of sleep are not voids of nothingness. They are the most fertile ground for our own creativity, our own healing, our own transformation. We live in a culture that is often deeply afraid of emptiness. We fill every moment with noise, with information, with distraction. We fear that if we stop, if we become still, we will be confronted with a terrifying void. But the wisdom of the quantum world and of the great contemplative traditions tells us that the opposite is true. It is in the silence that we can hear the subtle music of our own soul. It is in the emptiness that we can touch the source of all our creativity. Sleep is our nightly, sacred pilgrimage into this inner, creative void. As the external world of things and the internal world of ego structures dissolve, we are given the chance to connect with the pure, undifferentiated potential of our own being. This is not a passive state. It is a state of deep, unconscious processing, a state where the fragmented experiences of the day are integrated, where emotional wounds are cleansed, and where the seeds of new insights and new perspectives are sown. A dream is a virtual particle born from the vacuum of the mind. It is a fleeting, symbolic, and often mysterious expression of the deep creative processes that are at work in our inner silence. These dreams, like the virtual particles of the vacuum, can have real and powerful effects on our waking lives. They can bring us wisdom. They can bring us healing. They can bring us a new sense of purpose and direction. To learn to value silence, to befriend our own inner emptiness, to trust in the generative power of our own sleep, this is to align ourselves with the most fundamental creative principle of the universe. It is to understand that all true creation, whether of a galaxy, a work of art, or a new and more integrated self, is born not from frantic, effortful doing, but from a deep and patient surrender to the silent, secret, and life-giving power of the void. The quantum vacuum is not just out there in the vastness of space. It is in here, in the very ground of our own being. And every night, as we close our eyes and let go, we are returning home to this sacred, creative source. The quest to understand the universe and our place within it is a journey that has led us to the very frontiers of human knowledge, to the edge of space, of time, and of our own comprehension. We have grappled with the paradoxes of the quantum world, with the mysteries of dark energy and the multiverse, with the deep philosophical riddle of consciousness itself. And in this journey, we have discovered a universe that is far stranger, more beautiful, and more mysterious than our ancestors could ever have imagined. It is a universe born from a creative void, a universe of probability and potential, a universe that is not a static, clockwork machine, but a dynamic, evolving, and participatory reality. And we, as conscious, questioning, and dreaming beings, are not separate from this universe. We are an integral and essential part of its ongoing story. We are the universe's way of knowing itself, of feeling itself, of wondering at its own magnificent existence. The future of this quest is bright and full of promise. A new generation of powerful telescopes, of gravitational wave detectors, of particle accelerators will continue to push back the frontiers of our knowledge to provide us with new data, new insights, and, no doubt, new and even deeper mysteries. We are living in a golden age of discovery, a time when the answers to some of the oldest and most profound questions of humanity may be within our reach. But this quest is not just a scientific one. It is also a deeply personal and spiritual one. The insights of modern physics, with their emphasis on interconnectedness, on potentiality, on the participatory nature of reality, are not just abstract theories. They are also powerful and transformative metaphors for our own inner lives. They invite us to see ourselves not as isolated, separate egos, but as entangled, superpositional, and endlessly creative beings. They invite us to find the sacred in the silence, the potential in the emptiness, the wisdom in the uncertainty. And they invite us to honor the deep, mysterious, and restorative power of our own sleep. To see it not just as a biological necessity, but as a nightly pilgrimage to the quantum heart of our own being. A time to reconnect with the source of all creativity, all healing, and all change. The journey is far from over. The greatest discoveries, the most profound revelations, may still lie ahead, waiting patiently for us in the deep, silent, and beautiful darkness that lies just beyond the horizon of our current understanding. But the quest itself, the shared, human adventure to understand our cosmic home and our place within it, is a journey that gives our fleeting lives a meaning, a purpose, and a dignity that can rival the stars themselves. And as you close your eyes and let the universe of your own mind unfold in the quiet theater of your dreams, you can feel a sense of participation in this grand human adventure. The consciousness that is about to journey into the mysterious inner cosmos of sleep is the same consciousness that is, at this very moment, reaching out to the stars, listening for the echoes of creation, and striving to read the silent, beautiful, and endlessly fascinating story of the universe. Good night, and may your dreams be as vast and as wonderful as the cosmos itself. Reality is not as solid as it seems. Beneath the surface of what we call existence lies an intricate and beautiful web of rules. A set of principles so strange and counterintuitive that they defy the very logic we rely on in our everyday lives. Imagine a world where information is not just something we store on hard drives or write in books, but is a fundamental, physical, and a primary building block of reality itself. A world where the basic units of data are not fixed, definite ones and zeros, but are fluid, shimmering, and probabilistic entities, existing in a ghostly superposition of multiple states at once. This is a realm where the very act of observation, of looking at something, changes the nature of what is there. It is a world where two particles, separated by the vast, cold emptiness of galaxies, can be so deeply and mysteriously connected that the actions of one instantly, and without any apparent communication, affect the other. It is a world where a simple measurement can erase a universe of possibilities, collapsing the limitless into the defined, the potential into the actual. This is not the realm of science fiction, of fantasy, or of mystical speculation. This is the world as it is described by our best and most fundamental theory of nature, the theory of quantum mechanics. It is the foundation of the universe itself. For centuries, the clockwork, predictable order of classical physics painted a picture of a reality that was, at its core, understandable and intuitive. But as we have learned to probe deeper into the heart of matter, as our experiments have become more sensitive and our theories more sophisticated, we have found that the smallest scales of nature do not behave as our classical instincts tell us they should. They operate on a different logic, a different set of principles, a set of principles so bizarre that even Albert Einstein, one of the great architects of modern physics, struggled to accept them, famously dismissing one of its key features as spooky action at a distance. What if information is not just an abstract concept that we use to describe the world, but is the very scaffolding upon which reality is built? What if the universe is, in some deep and fundamental sense, a cosmic algorithm, a vast quantum computation that is constantly processing the fabric of existence itself? This is a radical and profound idea, one that is emerging from the confluence of physics, computer science, and information theory. It suggests that the its of the physical world, the particles, the fields, the forces, are all, at their core, manifestations of bits of quantum information. Yet, for all its strangeness and its deep philosophical mystery, the world of quantum information is not just a theoretical curiosity. It is a field that holds the potential to revolutionize our technology, to create new forms of computation, of communication, and of security that were previously unimaginable. It promises to give us unbreakable encryption, to build computers that can solve problems that are intractable for even the most powerful classical supercomputers, to create sensors of unprecedented precision. But could the strange and beautiful rules of quantum information also hold the answers to questions that are even more profound? Could the ultimate nature of reality itself be, at its core, an elaborate and beautiful interplay of quantum codes? Could consciousness, could life, could the very structure of space-time be emergent properties of an underlying informational reality? These are the questions that are driving the next great revolution in our understanding of the cosmos. The deeper we look, the stranger it becomes. The quantum world is a realm where our conventional, classical intuition crumbles into dust. And with it, our understanding of something as seemingly straightforward as information undergoes a profound and radical transformation. In classical physics, information is an abstract and secondary concept. It is something that we use to describe a physical system. It is the bits stored on a hard drive, the words written on a page, the positions and velocities of a set of particles. The information describes the reality, but it is not the reality itself. But in the quantum domain, this clear distinction between the physical system and the information it contains begins to dissolve. Quantum information takes on a physical and even primary identity. This physicality changes the very way we define and process information, endowing it with a strange and powerful set of new properties. Imagine a simple, classical bit of information, like the outcome of a coin flip. It is binary. It can be either heads or tails, a 1 or a 0. But a quantum bit, or qubit, the fundamental unit of quantum information, is not so constrained. Thanks to the principle of superposition, a qubit can be a 0, a 1, or, most remarkably, a ghostly, probabilistic blend of both at the same time. It is like a coin that is not heads or tails, but is spinning forever in a shimmering blur of both possibilities, until the moment it is measured. This non-binary nature of the qubit, its ability to exist in a continuous spectrum of states, adds an incredible complexity and power to the very notion of information. It means that a quantum system can store and process a vastly greater amount of information than its classical counterpart. This is not just a quantitative difference, it is a qualitative one. Quantum mechanics challenges the very deterministic perspective that underpins classical physics. A classical system, like a set of billiard balls on a table, is predictable. If you know the initial positions and velocities of all the balls, you can, in principle, calculate their entire future trajectory with perfect accuracy. But a quantum system is fundamentally, irreducibly probabilistic. You can never know its future with certainty. You can only know the probabilities of the different possible outcomes. This means that a quantum system is not just a matter of having enough data. It demands a complete reevaluation of how we interact with the universe, of the very nature of knowledge itself. Information, in this quantum picture, is not just a passive record of a pre-existing reality. It is an active, dynamic, and participatory entity, something that is woven into the very fabric of physical law. The theory of quantum mechanics suggests that all physical systems are, at their core, carriers of information. But this is not just descriptive, classical information. Quantum information has a set of strange and unique properties that set it apart. properties that enable transformations and processes that are simply impossible in the classical world. Take, for a moment, the concept of measurement. What actually happens when we look at a quantum system? This question strikes at the very heart of the measurement problem, one of the most contentious and deeply debated puzzles in all of quantum mechanics. As we have seen before it is observed, a quantum particle exists in a superposition of all its possible states. It is like an unread book, a book that contains every possible story, every possible narrative, all at the same time. The moment we read the book, the moment we make a measurement, we seem to force it to choose a single, definite story. The superposition collapses, and one of the many possibilities becomes the single, actual reality. But does this act of measurement represent the creation of information, or are we merely revealing a piece of a pre-existing, but hidden reality? The paradox deepens when we consider the nature of quantum states themselves. In the classical world, you can measure a property of a system, like the temperature of a cup of coffee, without fundamentally changing the system itself. But in the quantum world, this is not always the case. There are certain quantum states that cannot be fully known without destroying them. The very act of gaining information about the system can irrevocably alter it. Observation is not a passive act. It has a real physical cost. This forces us to rethink the very concept of truth or fact. Imagine two scientists trying to understand the state of a single electron. One scientist decides to measure its position with great precision. The other decides to measure its momentum. According to the uncertainty principle, they cannot both get a precise answer. The first scientist's measurement of the position makes the electron's momentum fundamentally uncertain. The second scientist's measurement of the momentum makes its position fundamentally uncertain. They are not just getting different, incomplete pieces of a single, objective picture. They are, in a sense, creating two different and mutually exclusive realities through their choice of measurement. The complementary nature of quantum systems, the fact that certain properties exist in a trade-off, ensures that our knowledge of the quantum world is always and fundamentally partial. It is not a limitation of our instruments. It is a built-in feature of reality. From this inherent uncertainty, we move to an even stranger and more profound quantum feature entanglement. When two or more particles become entangled, their individual quantum states are no longer independent. They merge into a single, shared state, a single wave function that describes the entire system, regardless of the distance separating the particles. Einstein, as we know, dismissed this as an eerie coincidence, a spooky action at a distance. But today, we know that entanglement is a real physical phenomenon. It binds particles together like invisible, non-local threads stretching across the vastness of the cosmos. Through this strange connection, one particle seems to know the state of its partner instantly, no matter how far apart they are. The measurement of one immediately influences the state of the other. The implications of this quantum entanglement for the nature of information are profound and revolutionary. It opens the door to technologies that were once the sole domain of science fiction: quantum teleportation, for example, is no longer a fantasy. It is a real, experimentally verified phenomenon. When two particles are entangled, it is possible to teleport the quantum state of a third particle onto one of the entangled pair, a process that effectively transfers the information across space without physically moving any matter. While this process does not allow for faster-than-light travel, the classical information needed to complete the teleportation process must still be sent at or below the speed of light. It is a phenomenon that fundamentally redefines our understanding of how information can be communicated. But the quantum world does not just offer new possibilities for information, it also imposes strict and beautiful new limits. The no-cloning theorem, a fundamental principle of quantum mechanics, states that it is impossible to create an identical, independent copy of an arbitrary, unknown quantum state. You cannot simply photocopy a qubit in the same way you can photocopy a classical bit. This is a profound and important feature of the quantum world. It ensures that quantum information has a kind of privacy and integrity that classical information lacks. It is the physical basis for the security of quantum cryptography. It also tells us something deep about the nature of reality. The universe, it seems, does not allow for perfect replication. Each quantum system is, in a sense, unique and unreproducible. The entangled pairs themselves carry their own unique measure of informational complexity, a quantity known as entanglement entropy. This entropy is a measure of the shared, non-local information between the particles, the degree of their interconnectedness. And it is this entanglement entropy that explains why. Despite the seeming magic of teleportation, entanglement cannot be used to send free, unlimited, and faster-than-light classical information. There are deep and beautifully consistent rules that govern the flow of information in the quantum world. Underpinning all of these strange and wonderful principles is the ever-present hum of the uncertainty principle. Heisenberg's revolutionary assertion that not all properties of a particle can be known with perfect precision at the same time. This is not just a limit on our knowledge, it is a fundamental feature of the information content of the universe itself. It places a cap on how much useful, classical information can be extracted from any quantum system at a given time. To encode and retrieve data in the quantum world requires a series of deliberate trade-offs, a kind of delicate balancing act that is dictated by the fundamental, complementary nature of reality. The complementarity principle, the idea that certain properties, like a particle's wave-like and particle-like nature, are mutually exclusive but equally necessary for a complete description, is the ultimate expression of this trade-off. You can ask a wave question, or you can ask a particle question, but you can never ask both at the same time. The information you gain about one aspect of reality necessarily costs you clarity in another. This is a profound departure from the classical worldview, where perfect, complete knowledge seems, at least in principle, to be attainable. In the quantum world, knowledge is inherently and beautifully incomplete. All of this complexity, all of this strangeness raises a deep and compelling question about the ultimate nature of reality. Is the universe at its core an informational entity? What if the physical world is not the fundamental reality, but is an emergent phenomenon, a manifestation of a deeper underlying quantum computation? This is not just an abstract philosophical speculation. It is an idea that is gaining traction in the world of theoretical physics. The process of decoherence, for example, can be seen as a kind of bridge between the quantum and classical worlds of information. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional, and entangled nature. The quantum information, the qubitness of the system, is not destroyed, but is rapidly spread out and dissipated into the vast number of degrees of freedom of the environment, becoming, for all practical purposes, irretrievable. This process is what explains why we do not see macroscopic objects like cats in a state of superposition. It is what allows the definite, classical world of our experience to emerge from the fuzzy, probabilistic world of the quantum. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. The idea of quantum information as being primary suggests that our universe might not just obey physical laws. It might embody them as a form of computation. The evolution of the universe, from the Big Bang to the present day, could be seen as a single, vast, and ongoing quantum computation. A process that is constantly processing information and creating new, more complex structures. In this view, particles are not just things, they are carriers of quantum information, data packets that are navigating a vast, cosmic computational architecture. This is a vision that transcends the classical idea of a universe composed of inert matter and forces. It imagines a universe that is, in a very real sense, alive with information. A universe that is constantly thinking, constantly computing its own reality into existence. And this vision has real, practical applications, particularly in the field of cryptography. The very properties of quantum information that make it so strange: superposition, entanglement. The no-cloning theorem are the same properties that make it the basis for a new and revolutionary kind of security: quantum cryptography, and specifically quantum key distribution, is a technology that uses the principles of quantum mechanics to create a provably secure communication channel. By encoding a secret key in the quantum states of single photons and sending them over an optical fiber, two parties can establish a shared random key that can be used to encrypt and decrypt their messages. The security of this system is guaranteed by the laws of physics. Any attempt by an eavesdropper to measure the photons will inevitably disturb their quantum state, a disturbance that can be immediately detected by the legitimate users. The randomness inherent in quantum measurement also provides a source of true, unpredictable randomness, which is a crucial ingredient for strong encryption protocols. As we look to the future, the development of a quantum internet, a global network that can transmit and process quantum information, could revolutionize not just our security, but our entire information infrastructure. It would be a network that is not just faster or more efficient, but is fundamentally different. A network that is built on the strange and beautiful logic of the quantum world itself. The journey into the heart of quantum information is a journey that is reshaping our deepest understanding of reality. It is a journey that ties together the abstract concepts of measurement, uncertainty, and entanglement, and reimagines them as the constituent parts of a single, unified, informational framework. And it is a framework that does not just describe reality, it actively determines it. From the security of our most sensitive communications to the most profound and existential questions about the nature of the cosmos, quantum information is shifting our perspective in deep and powerful ways. Could this be the true foundation of reality? Or is it merely a window into an even deeper, more mysterious layer of existence that is still awaiting our discovery? The tantalizing potential of this new science ensures one thing: this quantum narrative is far, far from over. From the relentless march of entropy and thermodynamics to the deepest and most profound mysteries of quantum mechanics, the concept of information serves as a crucial unifying thread, weaving its way through the vast and varied phenomena that define our physical world. To truly understand how profound and fundamental this concept is, we must first consider the intimate and beautiful relationship between information and entropy, a relationship that is at the very heart of the second law of thermodynamics. We see the effects of this law everywhere: the gradual crumbling of a mountain, the slow fading of a cherished memory, the inevitable cooling of a cup of coffee. Entropy is the universe's great, inexorable tendency towards disorder, towards a state of greater probability and lesser structure. It is the physical basis for the arrow of time. But here is where the story takes a fascinating turn. Information, in its purest, most fundamental sense, is a measure of order, of structure, of reduced uncertainty. When a physical system is in a highly ordered, low-entropy state, like a perfectly arranged deck of cards, We have a great deal of information about it. As the system evolves towards a state of higher entropy, as the cards are shuffled, this information is not destroyed, but is dispersed, becoming harder to access. The act of gaining information about a system, of making a measurement, is an act that can, at least locally, reduce its entropy, an act that brings order out of chaos. This beautiful and intricate dance between the disorder of entropy and the order of information was first given a rigorous mathematical form by the American engineer and mathematician Claude Shannon in his groundbreaking work on information theory in the 1940s. Shannon's work, which was originally designed to understand the limits of communication over noisy channels, provided a precise mathematical definition of information in terms of the reduction of uncertainty, and showed that it was deeply and formally connected to the concept of entropy in thermodynamics. This connection was deepened and made more physical by the work of the physicist Rolf Landauer in the 1960s. Landauer's principle, a cornerstone of the physics of information, established a fundamental link between the abstract, logical operation of computation and the concrete, physical world of energy and heat. Landauer showed that the erasure of a single bit of information from a computational system is not a purely logical act. It has a real physical cost. It must, by necessity, be accompanied by the generation of a small, but unavoidable, amount of heat, an increase in the entropy of the environment. This principle established, once and for all, that computation is not an abstract, disembodied process. It is a physical process, bound by the very same thermodynamic laws that govern the behavior of steam engines and chemical reactions. The metaphysical concept of information was thereby firmly and irrevocably tied to the tangible, material reality of the universe. This intimate relationship between information, entropy, and energy is beautifully illustrated in one of the most famous and enduring thought experiments in the history of physics. Maxwell's demon. In the 19th century, the physicist James Clerk, Maxwell imagined a tiny, intelligent being, a demon, who could control a tiny, frictionless door in a partition that divides a box of gas into two chambers. By observing the individual gas molecules, the demon could open the door to let the fast-moving, hot molecules pass into one chamber, and the slow-moving, cold molecules pass into the other. Over time, the demon could create a temperature difference between the two chambers, seemingly decreasing the entropy of the system in violation of the second law of thermodynamics. This paradox puzzled physicists for over a century. The solution, which was finally clarified in the 20th century with the development of information theory, lies in the information processing that the demon must perform. To do its job, the demon must first measure the velocity of each molecule, a process that requires the acquisition of information. It must then store this information in its memory. And finally, it must erase its memory to make room for the next measurement. And it is this act of erasing information that, according to Landauer's principle, must generate entropy, an amount of entropy that is at least as great as the entropy that was seemingly reduced by sorting the molecules. The second law is saved, but at a price. The thought experiment demonstrates, in a beautiful and profound way, how inseparable information is from the physical processes it describes. Information is not a ghostly, non-physical entity. It has a real physical substrate, and its manipulation has real physical consequences. This principle extends to the largest scales of the cosmos. The flow of information in our universe is fundamentally constrained by the laws of relativity. The speed of light is not just the maximum speed at which matter and energy can travel. It is the maximum speed at which information can be transmitted. This cosmic speed limit is what safeguards the principle of causality, the fundamental idea that a cause must always precede its effect. It ensures that the temporal order of events is preserved, that the past cannot be changed by the future. The very structure of space-time, with its fixed and universal speed of light, is a structure that is designed to regulate the flow of information, and it is at the intersection of relativity and information that we find one of the deepest and most challenging puzzles of modern physics. The black hole information paradox. When matter, with all its rich and complex information, falls into a black hole, it seems to be lost to the universe forever, trapped behind the one-way membrane of the event horizon. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be purely thermal, random, and devoid of any of the information that originally fell in. This would represent a fundamental violation of the quantum mechanical principle that information can never be truly destroyed. The resolution of this paradox is thought to lie in the subtle, quantum correlations and entanglements within the outgoing Hawking radiation, a solution that would require a deep and beautiful synthesis of quantum mechanics, general relativity, and information theory. Beyond the realms of classical physics, thermodynamics, and relativity, the role of information becomes even more central when we consider the dynamic, creative, and evolutionary processes of the universe. Despite the second law's relentless push towards greater disorder, the universe is not a uniform, featureless soup of entropy. On the contrary, it is filled with islands of astonishing and beautiful complexity, the intricate structures of galaxies, the fiery hearts of stars, the delicate and purposeful machinery of living organisms. These ordered structures are not a violation of the second law. They are a consequence of it. They are what the Nobel laureate Ilya Prigogine called dissipative structures, open systems that maintain their internal order by importing energy from their environment and exporting entropy. A star, for example, is a highly ordered system that maintains its structure by consuming the low-entropy fuel of hydrogen in its core and radiating high-entropy heat and light into the surrounding space. Life is the ultimate example of this process. A living organism is an island of incredible, localized order, a system that actively works to maintain its structure and to create new knowledge, all while increasing the overall entropy of the universe around it. The process by which these complex, ordered structures emerge is known as self-organization, and information is the silent guiding architect of this process. The flow of energy through a system is not enough to create complexity. There must also be an informational blueprint, a set of rules or constraints that guides the self-organizing process. In the formation of a snowflake, this blueprint is provided by the crystalline structure of water and the laws of thermodynamics. In the formation of a galaxy, it is provided by the laws of gravity and the initial density fluctuations in the early universe. And in a living organism, it is provided by the rich and unimaginably complex information encoded in the DNA molecule. This can be understood through the statistical interpretation of entropy, first developed by Ludwig Boltzmann. Boltzmann showed that the entropy of a system is related to the number of possible microscopic arrangements of its constituent parts that correspond to the same macroscopic state. A disordered, high-entropy state, like a shuffled deck of cards, is a state that can be realized in a vast number of different ways. An ordered, low-entropy state, like a deck of cards arranged in perfect numerical and suit order, is a state that can be realized in only one way. Information, in this picture, is what allows a system to find its way to these rare, improbable, and highly ordered states. The information in the DNA molecule, for example, guides the complex process of protein synthesis, ensuring that the right amino acids are assembled in the right order to create the functional machinery of the cell. It is a process that carves out a tiny, highly ordered path through a vast, chaotic landscape of possibility. The arrow of time, then, is a story of two competing tendencies. On the one hand, There is the relentless universal drive towards greater entropy, towards disorder and heat death. But on the other hand, there is the creative, local, and information-driven process of self-organization, a process that builds islands of exquisite and beautiful complexity against this cosmic tide. Life is the most remarkable and poignant expression of this creative countercurrent. It is a process that thrives by absorbing energy and processing information, a process that creates pockets of meaning and purpose in a universe that is, on the whole, becoming more meaningless and purposeless. And at the heart of this creative process lies the mysterious and powerful role of information. The principles of information are not just at play in the grand cosmic drama of stellar and biological evolution. They are also at the heart of the strange and beautiful world of quantum mechanics, at the smallest scales of reality. The very act of gaining information about a system, the act of measurement, is a process that fundamentally changes the state of that system. This is the basis of the thermodynamics of measurement, a field that explores the deep and intimate connection between information, entropy, and the quantum world. When we measure a property of a quantum particle, like its spin or its position, we are extracting information from it. But this is not a passive act. The measurement process itself is an irreversible, entropy-increasing interaction. It is the process by which the ghostly, probabilistic world of quantum superposition is collapsed into the definite, singular reality of our classical experience. The process of decoherence is the mechanism by which this happens. A quantum system is never truly isolated. It is always interacting, however subtly, with its environment. The information about its delicate superpositional state leaks out into the vast number of degrees of freedom of the surrounding world, becoming, for all practical purposes, irretrievably lost. This is what gives the quantum world its classical appearance. The definite, stable reality we perceive is a consequence of the constant entropic loss of quantum information into the environment. Perhaps one of the most exciting and forward-looking applications of these ideas is in the field of quantum computation. A classical computer processes information one logical step at a time, but a quantum computer, by harnessing the principle of superposition, can explore a vast number of computational paths simultaneously. This quantum parallelism gives it the potential to solve certain problems, like factoring large numbers or simulating complex quantum systems at a speed that is exponentially faster than any classical machine. This is a technology that could revolutionize science, medicine, and artificial intelligence. And as we look to the future, the frontier of information physics hints at even more radical and profound insights. Some researchers, in their quest for a theory of quantum gravity, have proposed that the very fabric of space-time may be, at its core, an informational construct. The holographic principle, for example, theorizes that all the information contained within a three-dimensional volume of space can be completely described by the information encoded on its two-dimensional boundary, like a hologram. If this is true, it would mean that information is not just a property of reality. It may be the very substance of reality itself. Furthermore, a deeper understanding of the thermodynamics of information could lead to a new generation of hyper-efficient technologies. By leveraging principles like Landauer's limit, we might one day be able to build computational and communication systems that operate at the absolute physical limits of energy efficiency. A future where our technological progress is guided not by the raw consumption of energy, but by the subtle and intelligent manipulation of information. And so, as our journey through the world of information comes to a close, we are left with a profound and tantalizing question. What if the universe itself is, at its most fundamental level, a vast, interconnected, and self-organizing field of information? If so, Then every star, every planet, every living being would be a constituent part of a grand cosmic informational matrix. A matrix that is constantly evolving, constantly learning, constantly creating new forms of order and complexity. Understanding this deeper, informational reality might not just unlock the next technological revolution. It might also reveal our true place in the intricate and beautiful dance of order, chaos, and knowledge. Information, once seen as a mere abstract description of the world, now emerges as the very scaffolding upon which the universe is built. From the inexorable increase of entropy to the creative process of self-organization, from the strange logic of the quantum world to the grand evolution of the cosmos. It is the thread that illuminates our path towards a deeper and more unified understanding of what energy and matter alone could not explain. As we continue to probe the mysteries of information and its physical manifestations, one thing becomes clear: the story of the universe is not just about what it is made of, but about what it communicates. And in learning to read this cosmic message, we are not just deciphering the secrets of the universe. We are, in a very real sense, discovering our own. Life, at its very essence, can be understood as a profoundly sophisticated and ancient information processing system. Every single cell in your body, from the neurons in your brain to the muscle fibers in your heart, operates like a tiny, powerful, and exquisitely designed biological computer, constantly handling a vast and complex flow of information to sustain the miracle of your existence. And the source code for this incredible biological software is not written in silicon, but in the elegant double helix structure of the DNA molecule. DNA is not just a chemical, it is nature's own time-tested programming language, a biological script that has been written, edited, and refined over the course of nearly 4 billion years of evolution. This single, remarkable molecule, present in almost every cell of your body, contains the complete set of instructions, the architectural blueprint, that guides everything from the division of your cells to the synthesis of the proteins that are the workhorses of your biological machinery. It is a vast and ancient library of life, a library where every book is a gene, and every chapter contains a piece of the accumulated evolutionary wisdom of your ancestors. The process of evolution itself can be seen as the ongoing editing and refinement of this great genetic library. Through the random, mutational process of trial and error, life is constantly experimenting with new editions of its own chapters. Random changes in the genetic information, mutations, recombinations, and the more subtle epigenetic modifications that can be influenced by the environment create a constant stream of new variations. Natural selection then acts as a harsh, but ultimately creative, editor. Those variations that happen to provide a survival or reproductive advantage in a particular environment are preserved and passed on to the next generation, while those that do not are discarded. This process, repeated over countless generations, is not just a random walk through the space of possibility. It is a powerful optimization algorithm, a process that allows life to learn, to adapt, and to accumulate an ever-growing repository of knowledge about how to thrive in an often hostile and unpredictable universe. These principles of biological information processing are not just metaphorical. They are deeply and formally connected to the mathematical principles of information theory, a field that was originally developed to understand the transmission of data in man-made communication systems. The rules of information fidelity, of redundancy, of error correction, are just as relevant to the replication of a DNA molecule as they are to the transmission of a digital file over the internet. The genetic code, for example, is brimming with built-in safety mechanisms. It has a degree of redundancy, where multiple different codons can code for the same amino acid, providing a buffer against some mutations. And our cells have evolved a sophisticated and complex machinery of DNA repair enzymes. molecular proofreaders that constantly scan the genome for errors and correct them, ensuring that the vital instructional information is preserved with an incredible degree of fidelity. But this stability does not stifle evolution. On the contrary, it provides the stable, reliable foundation upon which the creative process of variation and selection can occur. The story of life's information processing continues in the intricate, dynamic, and beautiful networks of communication that exist within and between our cells. The flow of information from the genetic archive of the DNA to the functional machinery of the cell is a marvel of molecular engineering. In a process called transcription, a segment of the DNA is copied into a messenger RNA molecule. This mRNA molecule then travels out of the nucleus and into the cytoplasm, where, in a process called translation, its sequence is read by a molecular machine called a ribosome, which assembles a specific protein, amino acid by amino acid, according to the genetic instructions. This is the central dogma of molecular biology, the fundamental flow of information from DNA to RNA to protein. And it is a process that is happening trillions of times a second in your body right now. The way our cells process this vast amount of data is a masterclass in decentralized, distributed computing. There is no central processing unit, no single brain of the cell. Instead, the cell is a complex, self-organizing network of interacting molecules, a symphony of biochemical signals where each part is in constant communication with the whole, allowing the cell to respond and adapt to its constantly changing environment in a remarkably efficient and robust way. The role of information in building the complexity of life becomes even more apparent when we consider the great evolutionary transition from single-celled organisms to multicellular life. This was a leap that required a complete and radical restructuring of how biological information is stored, processed, and transmitted. Multicellular organisms had to invent new ways to coordinate the functions of billions and even trillions of interconnected cells to ensure that they all work together for the good of the whole. The emergence of the nervous system was a key innovation in this process. The neural network of an animal is an advanced biological supercomputer, a system that is dedicated to processing the vast amount of sensory information from the environment, to driving complex behaviors, and to fostering the process of decision-making. But life's ingenuity in information processing is not limited to the top-down control of neural systems. At the other end of the biological spectrum, we find phenomena like horizontal gene transfer in bacteria, a process where single-celled organisms can directly exchange genetic information with each other, even across species boundaries. It is a kind of biological internet, a peer-to-peer network that allows for the rapid spread of useful genetic innovations, like antibiotic resistance, through the microbial world. These different strategies, the centralized processing of a nervous system and the decentralized network of horizontal gene transfer, are both powerful examples of how life, at every scale, is constantly experimenting with new and more efficient ways to handle the challenges of evolutionary adaptation. Adaptation itself, at its very core, is a process of changing how information is processed and utilized. Organisms are not passive slaves to their genetic programming. They are active, learning systems that are constantly adjusting their internal and external information strategies in response to the pressures of their environment. The process of learning and memory, for example, which is so highly developed in species like birds and mammals, is a powerful adaptive mechanism. It allows an organism to store information about its past experiences, the location of a food source, the presence of a predator, and to use that information to make better, more informed decisions in the future. The environment itself acts as a constant stream of feedback, a set of data that shapes and refines these learning processes, forcing life to operate like a complex, adaptive algorithm that is constantly working to maximize its efficiency and its chances of survival. The influence of information becomes even more profound and fascinating when we consider how these evolutionary processes extend beyond the realm of biology and into the realm of culture and cognition. The evolution of language in human beings, for example, was not just the development of a new way to make sounds. It was a revolutionary leap in the technology of information storage and transmission. Language allowed knowledge to be accumulated, shared, and built upon across generations. A process that is far more rapid and powerful than the slow generational transfer of genetic information. Language is, in a very real sense, a form of externalized biological information. A mimetic code that has allowed human culture to evolve and adapt at a breathtaking pace. And over the course of our history, we have continued to extend the principles of biological information processing into our artificial systems, from the invention of writing and the printing press to the development of the digital, computational marvels that define our modern world. Even the nature of intelligence itself is deeply and inextricably tied to the way that organisms process and utilize information. The increased complexity of the neural connections in the brains of so-called intelligent species is a direct reflection of the growing need to analyze, to store, and to respond to an ever-increasing amount of data from a complex and ever-changing environment. Human cognition, and by extension, human intelligence, has co-evolved with these powerful information processing abilities. To be intelligent is not just to be able to think, it is to be able to efficiently acquire, to analyze, to synthesize, and to translate information into effective, purposeful action. Understanding these deep and beautiful connections between biology, information theory, and evolution paints a new and compelling portrait of life. It is a narrative of constant change, of relentless refinement, and of beautiful adaptation. A narrative in which information lies at the very heart of everything. Life does not evolve randomly. It evolves systematically, constantly finding new and more ingenious ways to process, to store, and to leverage its vast and growing informational wealth in order to thrive against the odds. The evolutionary journey of life, from the first self-replicating molecule to the complex, global civilization of our own species, is not just a story of the survival of the fittest. It is the story of the survival of the most informationally adept. And as we stand at this unique moment in history, as we begin to create new, artificial forms of intelligence, we are not just continuing this evolutionary process. We are, perhaps, on the verge of accelerating it in ways that are both thrilling and deeply, profoundly unsettling. The story of life is the story of information, and it is a story that is far, far from over. The quantum phenomenon of entanglement is not just a strange and counterintuitive curiosity of the subatomic world. It is an experimentally verified reality, a feature of the cosmos that forces us to fundamentally reevaluate our classical notions of space, of distance, and of connection. It is the discovery that two or more particles can share a single, unified quantum state, a relationship so profound and immediate that it seems to challenge the very locality of reality. The idea that objects can only be influenced by their immediate surroundings. But this is where the story gets even stranger. The concept is so bizarre that it deeply troubled even Albert Einstein, who, along with his colleagues Boris Podolsky and Nathan Rosen, famously labeled it spooky action at a distance. In their 1935 paper, they constructed the EPR paradox, a thought experiment designed to show that the predictions of quantum mechanics were so strange that the theory must be incomplete. They argued that if quantum mechanics was right, then particles could seemingly communicate faster than the speed of light, a clear violation of one of the most fundamental principles of his theory of relativity. For Einstein, this spookiness was a sign that there must be some local hidden variables, some unknown properties that the particles carried with them, that were predetermining the outcomes of the measurements, thus preserving the comforting classical notion of locality. For decades, this was a philosophical debate, but in the 1960s, the physicist John Bell, in a stroke of brilliant insight, formulated a mathematical theorem, now known as Bell's theorem, which provided a way to experimentally test the predictions of quantum mechanics against any possible local hidden variable theory. Bell's theorem, and the numerous increasingly precise Bell test experiments that have been performed in the decades since, have delivered a stunning and unambiguous verdict. The inequalities derived by Bell have been overwhelmingly violated, time and time again, confirming the non-local predictions of quantum mechanics and ruling out the possibility of any local hidden variable explanation. The spooky action is real. The universe is, in some deep and fundamental way, non-local. This does not mean that we can use entanglement to send faster-than-light signals and violate causality. But the underlying instantaneous connection is undeniably there. It tells us that our intuitive picture of a universe made up of separate, independent objects is an illusion. The answer to how this happens lies in the strange nature of quantum measurement. When we observe or measure one of the entangled particles, its wave function, the cloud of its possibilities, collapses and it settles into a definite state. And because the two particles are part of a single, unified quantum system, this collapse is not a local event. The entire entangled wave function collapses at once, and this means that the state of the distant, unmeasured partner is also instantly determined. This phenomenon of wave function collapse raises profound questions about the role of the observer in defining reality. Is the universe fundamentally deterministic, with the collapse just revealing a pre-existing state? Or does the act of observation itself play a creative role in shaping the outcome? This brings us to the concept of decoherence, a process that helps to bridge the gap between the strange, superpositional world of the quantum and the definite, classical world of our experience. Decoherence explains how a quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence, its ability to be in a superposition of states. The information about the superposition leaks out into the environment, making it practically impossible to observe. This is why we do not see macroscopic objects in a state of superposition. But decoherence does not fully solve the measurement problem, it just pushes it back. Different interpretations of quantum mechanics, from the traditional Copenhagen interpretation to the radical many worlds interpretation, continue to wrestle with this deep, conceptual riddle. The profound implications of quantum entanglement extend far beyond the realm of theoretical physics and into the world of revolutionary new technologies. The strange, non-local connection between entangled particles is not just a philosophical puzzle. It is a powerful new resource that we are just beginning to learn how to harness. Take, for example, the field of quantum cryptography. The security of our current classical communication systems is based on the computational difficulty of solving certain mathematical problems, like factoring large numbers. But a sufficiently powerful quantum computer could, in principle, solve these problems easily, rendering much of our current encryption obsolete. Quantum cryptography offers a new and fundamentally more secure paradigm. By using entangled photons to create a secret, shared key between two parties, a process known as quantum key distribution, it is possible to create a communication channel whose security is guaranteed not by computational complexity, but by the fundamental laws of physics. Any attempt by an eavesdropper to intercept and measure the photons will inevitably disturb their entangled state, a disturbance that can be immediately detected by the legitimate users. It is a system that is, in principle, unhackable, Similarly, the phenomenon of quantum teleportation, once the stuff of science fiction, is now a routine, if still small-scale, laboratory experiment. It uses the principles of entanglement to transfer the complete quantum state of a particle from one location to another, without physically moving the particle itself. This is not the beaming up of Captain Kirk, but it is a revolutionary new way to think about the transmission of information, a process that could one day be the foundation of a quantum internet, a global network that can transmit and process quantum information. And it is in the field of quantum computing that the power of entanglement is most fully realized. A classical computer processes bits of information that are either a 0 or a 1. A quantum computer uses qubits, which can be in a superposition of both. But the true power of a quantum computer comes from its ability to entangle these qubits. By entangling a large number of qubits, a quantum computer can create a vast, multidimensional computational space, allowing it to explore an astronomical number of possibilities simultaneously. This quantum parallelism is what gives a quantum computer the potential to solve certain problems, from designing new drugs and materials to breaking complex codes at a speed that is exponentially faster than any classical machine. The strange, non-local bond of entanglement is what allows the qubits to work together in a coherent, powerful harmony, unlocking a level of computational power that was previously unimaginable. But what if the significance of entanglement extends even beyond the realms of technology and into the very fabric of space-time itself? Some of the most exciting and speculative ideas in modern theoretical physics suggest that entanglement may not just be a phenomenon that happens in space-time, it may be the very thing that creates space-time. The ER equals EPR conjecture, proposed by the physicists Juan Maldacena and Leonard Susskind, is one of the most provocative of these ideas. It suggests a deep and surprising equivalence between two seemingly disparate concepts, quantum entanglement and wormholes. The conjecture posits that when two particles are quantum mechanically entangled, they are, in a sense, connected by a microscopic wormhole. This is a staggering idea. It suggests that the strange, non-local connection of entanglement is actually a manifestation of a deeper, geometrical connection in a higher dimensional space. It implies that the geometry of spacetime is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is woven from the intricate and complex web of quantum entanglements between the fundamental constituents of the universe. In this view, space is not the thing that separates us. It is the thing that connects us. A vast network of quantum threads, this idea, while still highly theoretical, provides a powerful and beautiful new lens through which to view the universe. It offers a potential path towards a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. It suggests that the deep puzzles of quantum mechanics and the deep puzzles of general relativity may be two sides of the same informational coin, and it has profound philosophical implications. If the fabric of reality is woven from the threads of entanglement, then the universe is not a collection of separate, independent objects, but a single, holistic, and deeply interconnected whole. This is a worldview that resonates with the deepest intuitions of many spiritual and contemplative traditions. The idea that we are all one is not just a poetic sentiment. It may be a deep, physical truth, a truth that is written in the non-local, entangled language of the cosmos itself. The implications of this for our own human experience are vast and largely unexplored. If our own consciousness is, as some have speculated, a quantum phenomenon, then we too may be part of this universal entangled web. The feelings of empathy, of connection, of collective consciousness may not be just psychological phenomena, but may have a real, physical basis in the entangled nature of our own being. Imagine a future where entanglement is not just a topic for the laboratory, but a practical and integrated part of our everyday lives. Our most sensitive data is transmitted with perfect security through quantum-encrypted networks. Quantum computers are solving some of humanity's most pressing problems, from climate change to disease, and perhaps even our understanding of ourselves, of our own interconnectedness, will have been transformed by this deep quantum insight, for all its promise. Entanglement reminds us that the universe retains its deep and beautiful mysteries. It challenges our most basic intuitions about causality, about distance, about reality itself. It urges us to rethink our place in a cosmos where the boundaries between here and there, between now and then, between self and other, may be far more fluid and far more mysterious than we ever imagined. What we have uncovered so far is merely the tip of a vast and magnificent iceberg. And with each new experiment, with each new theoretical insight, the strange and beautiful world of quantum entanglement continues to provoke, to puzzle, and to inspire. It is an invitation, not just to scientists, but to all of us, to look closer, to think deeper, and to imagine a universe that is far more interconnected and far more wonderful than it first appears. The universe is a sprawling and often bewildering enigma, a puzzle that has captivated the greatest minds of humanity for centuries. We have observed its patterns, we have dissected its laws, and we have spun beautiful, intricate theories about its origins and its destiny. But what if we were to tell you that the very fabric of reality itself could be understood in a radically new and powerful way? What if the universe, in all its vastness and complexity, operates not like a grand clockwork machine, but like a colossal and unimaginably powerful quantum computer? This is a paradigm-shifting idea, one that is emerging from the frontiers of theoretical physics and computer science. It is a vision that reframes our understanding of reality, suggesting that at its most fundamental level, the cosmos may not be made of matter and energy, but of information, and that the laws of physics are not just a set of static rules, but are a form of ongoing, dynamic computation. This concept of a computational universe blurs the line between the observer and the observed, between the physical and the informational, in a way that is both deeply challenging and profoundly beautiful. At the heart of this new paradigm lies a radical reinterpretation of the laws of physics themselves. The equations and the constants that we have so carefully mapped, from the elegant mechanics of Newton to the curved space-time of Einstein and the probabilistic waves of quantum mechanics, may be better understood not as a description of reality, but as the operating system for reality. They are the rules, the algorithms, that govern how the state of the universe is processed and evolved from one moment to the next. Quantum mechanics, in this picture, becomes the fundamental programming language of the cosmos. It is a language that is not deterministic, but probabilistic. It does not deal in absolute certainties, but in a rich and complex landscape of possibilities. The wave function of a quantum system is not just a mathematical tool, it is a complete, informational description of that system, a catalog of all its potential states. And the process of measurement, the infamous collapse of the wave function, is a computational step, a moment when the vast, superpositional potential is processed and a single, definite output is rendered into our classical reality. The ongoing mathematical dance of quantum mechanics is what gives the universe its structure, its texture, and its very existence. Look deeper into this computational cosmos, and you will find the principle of quantum superposition, the astounding ability of a particle to exist in multiple states simultaneously. If you have heard of Schrödinger's cat with its ghostly existence between life and death, you have already grasped the central paradox of this concept. But on a computational level, superposition is not a paradox. It is a resource, It is the basis for a massive and natural form of parallel processing. A classical computer must handle a computation one step at a time in a linear sequence. But a quantum system, by virtue of its ability to exist in a superposition of all possible states, can explore a vast number of computational paths all at once. This opens up a breathtaking possibility. What if the universe itself is performing a kind of continuous, massive parallel computation? What if every quantum event, every collapse of a wave function, is a moment of information processing, creating ripples of newly computed reality that propagate through the cosmos? This would suggest that the universe has an inherent and almost unimaginable computational efficiency, a power that is far beyond anything we could ever hope to achieve with our own man-made technologies. Central to this model of a computational universe is the role of measurement. As we have seen, a quantum system exists as a cloud of possibilities until an observation forces it to collapse into a single, definitive state. In the same way, a computation is not just a sequence of potential solutions. It must, at some point, result in a definite output. The observer in this picture is not just a passive element of reality. They are an active and perhaps even necessary participant. Every time we make a measurement, every time we interact with the world in a way that resolves a quantum uncertainty, we are, in a sense, contributing to the ongoing computation of the universe's state. We are not just reading the cosmic code, we are helping to write it. But what happens when errors arise in this incredible cosmic system? Just as our own computers are prone to glitches and bugs, the universe is not immune to the disruptive influence of quantum noise and decoherence. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate superpositional nature. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. This could be seen as a form of error. But what if the universe has a built-in mechanism for quantum error correction? This is a concept that is at the very forefront of the development of real-world quantum computers. The idea of encoding quantum information in a redundant way, so that it can be protected from the effects of decoherence. Could it be that the universe itself employs a form of natural quantum error correction? Could the remarkable stability and consistency of our physical laws be a consequence of an inherent informational redundancy in the fabric of reality? A system that is constantly correcting errors as they arise and preserving the deep computational integrity of existence. The computational nature of the universe is also reflected in the strange, non-local structure of quantum causality. In our classical world, cause and effect follow a clear linear chain of events. But in the quantum realm, as we have seen with entanglement, the relationships between events can be far more subtle and interconnected. Entanglement creates a form of spooky, non-local connection between particles that defies our classical intuition about space and distance. If we translate this into a computational model of the universe, it suggests that the flow of information may not be a simple, linear process. It may follow the intricate, entangled pathways of the quantum world. The processing of reality is not a straight line, but a complex, interconnected web, a graph of relational information where the state of one part can instantly influence the state of another, no matter how far apart they are. This leads to an even more radical idea. What if space-time itself is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is born from the processing of quantum information? Some of the most advanced theories of quantum gravity, like the holographic principle, suggest that the three-dimensional space we experience may be a projection, a hologram that is encoded on a two-dimensional informational surface at the boundary of our universe. In this view, the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space, the flow of time, the force of gravity. All of these could be emergent properties of a deeper, underlying quantum computation. We can see hints of this computational logic even in the processes of the natural world. Quantum algorithms, like Shor's algorithm for factoring numbers or Grover's algorithm for searching a database, are specific, highly efficient solutions that are optimized for quantum systems. And intriguingly, some of these quantum computational strategies share deep structural parallels with natural processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field. It is as if nature itself has, over billions of years of evolution, discovered and implemented some of the most efficient quantum algorithms. This brings us to the most tantalizing and most speculative hypothesis of all. If the universe is indeed a quantum computer, could reality itself be an intricately coded simulation? The simulation hypothesis. The idea that our entire existence might be a program running on a vast cosmic computer is one that has long been a staple of science fiction, but it is now being seriously considered by some physicists and philosophers. If this were true, it would provide a natural explanation for some of the strange, built-in limits of our universe, like the speed of light or the Planck length. These would not be arbitrary constants, but would be the processing speed and the pixel size of the underlying computational reality. The view of the universe as a quantum computational system does not just reframe our understanding of the physical world. It opens up vast, new frontiers for exploration. It forces us to reconsider age-old philosophical questions in the new and powerful light of physics and computer science. If the universe is computing reality, then to understand that computation would be to understand the ultimate nature of existence, and perhaps it would grant us an unprecedented ability to interact with and to shape that reality, to move from being just a variable in the cosmic algorithm to becoming one of its programmers. This perspective does not reduce the awe and wonder of existence. It enhances it. It imagines a cosmos that is alive with a ceaseless and almost unimaginably complex process of calculation, a universe that is mathematically encoding and processing every atom, every star, every galaxy. And it is a reality in which you, the conscious observer, are a crucial and integral participant, not a passive recipient of information, but a node in the network, influencing the system and being influenced by it, connected through the invisible, entangled threads of quantum information to every other part of this incredible, unending equation. Imagine for a moment that this vast, three-dimensional universe, with all its depth, its substance, its seemingly solid reality, is not as it seems. What if everything we experience, the space that separates us, the time that flows around us, the very matter that makes up our bodies, is an elaborate and beautiful projection, a cosmic hologram? What if our entire, rich, three-dimensional world is, in fact, a higher-dimensional mirage? Its information compressed and encoded onto a simpler, two-dimensional canvas at the very edge of our cosmos. This startling and deeply counterintuitive idea is at the heart of what physicists call the holographic principle. And it is a concept that challenges the very fabric of reality as we know it, suggesting a universe that is fundamentally informational, a universe where the distinction between the container and the contained, between the boundary and the bulk, is not as clear as we once thought. The origins of this revolutionary idea lie in one of the most unlikely and most mysterious corners of the cosmos, the study of black holes. For decades, black holes were seen as the ultimate information destroyers. Their immense gravity creates an event horizon, a one-way membrane from which nothing, not even light, can escape. Any information that falls into a black hole seems to be lost to the universe forever. a direct violation of the fundamental quantum mechanical principle that information can never be truly destroyed. In the 1970s, the physicist Jacob Bekenstein, and later Stephen Hawking, discovered something remarkable. They found that the entropy of a black hole, a measure of its information content, is not proportional to its three-dimensional volume, as one would expect, but is proportional to the two-dimensional area of its event horizon. It is as if all the information about the three-dimensional objects that have fallen into the black hole is somehow stored or encoded on its two-dimensional surface. This was the first hint of the holographic principle. It was a suggestion that the information content of a region of space is not as extensive as it seems, that it can be fully described by a theory that lives on its boundary. This idea was given a precise mathematical form in the 1990s by the physicist Juan Maldacena in what is now known as the ADI-CFT correspondence. This is a profound and powerful duality, a kind of mathematical Rosetta Stone that shows a precise equivalence between two, seemingly very different, physical theories. On one side of the duality, we have a theory of gravity, like string theory, that lives in a curved, five-dimensional anti-de Sitter space. On the other side, we have a quantum field theory, a conformal field theory that has no gravity and lives on the flat, four-dimensional boundary of that space. The correspondence states that these two theories are completely equivalent. Every question you can ask in the five-dimensional gravitational theory has a corresponding and equally valid question in the four-dimensional quantum field theory on the boundary. This is a stunning and revolutionary idea. It suggests that gravity itself, which we have long considered to be one of the fundamental forces of nature, may not be fundamental at all. It may be an emergent phenomenon, a holographic projection of a deeper non-gravitational quantum reality that lives on a lower dimensional surface. The three-dimensional world of our experience, with all its gravitational complexity, could be a hologram generated by the quantum interactions of particles on a distant two-dimensional screen. This holographic vision of the universe has profound implications for our understanding of space and time. If the geometry of space-time is an emergent holographic property, then it may not be a smooth, continuous fabric at its most fundamental level. It may be quantized, made up of discrete, indivisible units, like the pixels on a computer screen. The search for this holographic noise, the subtle quantum graininess of space-time, is an active, if highly challenging, area of experimental physics. High-energy experiments at particle accelerators and precise, astronomical observations of the cosmic microwave background are both searching for the faint, indirect clues that could reveal the pixelated nature of our reality. If the holographic principle holds true, it would also force us to rethink our most basic notions of causality and locality. In a holographic universe, the idea that events are determined by their local causes and effects may no longer be the fundamental story. The unfolding of events in our three-dimensional bulk would be dictated by the complex, non-local quantum correlations and entanglements of the information on the two-dimensional boundary. The universe would be, in a very real sense, a holistic and interconnected system, where the part is always a reflection of the whole. This perspective also offers a new and powerful way to think about the nature of gravity itself. The physicist Eric Verlinde, building on the holographic principle, has proposed that gravity is not a fundamental force, but is an entropic force. It is an emergent phenomenon that arises from the thermodynamic principles of information. In this view, gravity is a consequence of the universe's tendency to maximize its entropy, a statistical force that pulls things together because it is the most probable configuration of the underlying informational degrees of freedom. This is a beautiful and compelling idea, one that connects the geometry of space-time directly to the laws of information and thermodynamics. And the mathematical architecture for exploring these holographic ideas is provided by the powerful framework of quantum field theory, and particularly conformal field theory. These theories describe how the information on a lower dimensional boundary can give rise to the rich and dynamic phenomena of a higher dimensional space. The study of these intricate mathematical mappings is one of the most exciting and productive areas of modern theoretical physics, and it is providing us with new and powerful insights into the deep, and as yet unsolved, challenge of quantum gravity. The holographic principle offers a compelling and beautiful starting point for unifying the two great and seemingly incompatible pillars of modern physics, general relativity and quantum mechanics. It suggests that they may be two different, dual descriptions of the same underlying informational reality. Beyond its revolutionary implications for physics, the idea of a holographic universe raises a host of deep and unsettling philosophical questions. If our familiar three-dimensional world is, in some sense, an illusion, a projection of a more fundamental two-dimensional reality, then what does this say about the nature of existence itself? Are we, as conscious three-dimensional beings, just complex patterns in a cosmic hologram? What are the ultimate limits of our knowledge, if the reality we are trying to understand is not the fundamental one? These are questions that push the boundaries of science and steer us into the deep, and often murky, waters of metaphysics, of epistemology, and of existentialism. The holographic principle is a profound and humbling reminder of the potential limitations of our own evolved cognition. Our senses, our brain, have been shaped by the pressures of natural selection to be effective tools for surviving and reproducing in a three-dimensional macroscopic world. They are not necessarily designed to perceive the ultimate, fundamental nature of reality. The world we experience is a user interface, a simplified, and likely very partial, representation of a much deeper and far stranger underlying reality. But it is this very drive to question, to look beyond the surface, to strive for a deeper understanding, that is the hallmark of our species. The holographic principle also invites us to reconsider our picture of science itself. Science is not a process of uncovering a single, fixed, and absolute truth. It is an evolving narrative, a story that we refine and rewrite with every new discovery. The idea that even our most fundamental concepts, like space and time, could be emergent, and perhaps even illusory, is a powerful testament to the open-ended and self-correcting nature of the scientific process. It teaches us that we must be prepared to question everything, to hold our most cherished theories with a degree of humility, and to be open to the possibility that the next great revolution in our understanding will come from a place we least expect. As we gaze into the deep mysteries of the universe, from the swirling, information-scrambling event horizons of black holes to the subtle, quantum fabric of space-time itself, the holographic principle stands as a beacon of what science can achieve when it dares to challenge its own most fundamental conventions. It is more than just a theory. It is a testament to the boundless creativity and the relentless curiosity of the human mind. And as we continue to explore the implications of this strange and beautiful idea, we are not just decoding the secrets of the cosmos, we are also, in a very real sense, decoding ourselves and our own mysterious and holographic place within the grand and perhaps illusory cosmic drama. The reality we perceive, with its solid objects, its linear flow of time, and its clear causal relationships, is like a beautifully woven and seemingly complete tapestry. But what if, on closer inspection, we find that the threads are not as tightly knit as they appear? What if we discover gaps, tears, and strange, unexplored patterns in this fabric we call existence. The journey into the heart of modern physics is a journey into this very realization. It is the discovery that our classical, common-sense picture of the world is a powerful, but ultimately limited, approximation of a much deeper, stranger, and more mysterious reality. And it is a journey that leads us to one of the most enigmatic questions of all. Can we ever fully and completely decode the true nature of reality? The first and most profound challenge to our classical worldview comes from the quantum realm. The concept of an objective reality, the idea that the world exists with definite properties, independent of our observation of it, seems, at first glance, to be an obvious and necessary starting point for any scientific inquiry. A tree in the forest is a tree, whether we are there to see it or not. But quantum mechanics, with its strange logic of superposition and measurement, complicates this simple picture. The observer effect demonstrates that the very act of measuring a quantum system can alter its state. An electron does not have a definite position until we measure it. Before the measurement, it exists as a wave of probability. Our observation forces this wave to collapse into a single, definite location. It is as though the universe only paints the picture of reality once we decide to look at the canvas. This raises a deep and unsettling question: how much of what we perceive as real is a property of the world itself, and how much is a product of our interaction with it, a reflection of the questions we ask and the measurements we make? This inherent fuzziness of the quantum world is quantified by Heisenberg's uncertainty principle. At the most fundamental level, it is impossible to simultaneously know certain pairs of properties of a particle, like its position and its momentum, with perfect accuracy. The more precisely we know one, the less we can know about the other. This is not a limitation of our instruments. It is an intrinsic, built-in feature of nature. It is as if reality itself has a fundamental blurriness at its core, a limit to its own definiteness. This suggests that our quest for a complete and perfectly precise knowledge of the universe may be, in principle, an impossible one. This fundamental limit on our knowledge is not just a feature of the physical world, it is also a feature of the abstract, mathematical world we use to describe it. In 1931, the logician Kurt Gödel, in one of the most stunning intellectual achievements of the 20th century, proved his incompleteness theorems. These theorems show that in any sufficiently complex and consistent mathematical system, there will always be true statements that cannot be proven. Within the rules of that system, mathematics, the very language of science, the tool we use to build our theories of reality, is itself fundamentally and forever incomplete. This has profound implications. If even the abstract logical framework we use to understand the universe has inherent, unprovable truths, how can we ever hope to build a final, complete theory of everything? Gödel's work suggests that our knowledge will always be a work in progress, a system that can be made more complete only by introducing new and themselves unprovable axioms. The quest for an absolute final foundation for our knowledge is a logical impossibility. This inherent incompleteness of our theoretical frameworks is reflected in the ongoing and often contentious debates about the interpretation of quantum mechanics itself, the Copenhagen interpretation, the many worlds interpretation, Bohmian mechanics. Each of these offers a different and seemingly incompatible picture of the underlying reality of the quantum world. Each is a different and partial attempt to make sense of the same strange set of experimental results. The fact that, after a century of debate, there is still no consensus on which, if any, of these interpretations is correct is a powerful testament to the deep, and perhaps irreducible, mystery that lies at the heart of our most fundamental theory. But the limits of our knowledge are not just found in the bizarre world of the quantum or the abstract realm of mathematics. We also encounter them, when we try to bridge the gap between the simple and the complex, between the microscopic and the macroscopic. This is the problem of emergence. The philosophy of reductionism, which has been a powerful and successful guiding principle in science, is the idea that we can understand a complex system by breaking it down into its simpler constituent parts. We can understand the properties of a gas by understanding the behavior of its individual molecules. We can understand the chemistry of a protein by understanding the properties of its atoms. But this approach has its limits. There are many complex systems, from the flocking of birds to the functioning of a city, from the intricate folding of a protein to the emergence of consciousness in a brain, where the behavior of the whole seems to be more than just the sum of its parts. These systems exhibit emergent properties, novel and unpredictable behaviors that arise from the complex, nonlinear interactions of their many components. You cannot understand the beauty and complexity of a flock of starlings by studying a single starling in a cage. You cannot understand the subjective experience of consciousness by studying a single neuron under a microscope. The bridge between the microscopic laws of physics and the macroscopic, emergent realities of our world remains one of the great unsolved frontiers of science. The challenge of understanding complexity is not just a conceptual one, it is also a computational one. The idea that we could, in principle, simulate the entire universe on a powerful enough computer and thus uncover all its secrets is a tempting one. But the theory of computational complexity suggests that this may be an impossible dream. There are many systems in nature that are computationally irreducible. This means that there is no shortcut, no simpler calculation that can predict their future behavior. The only way to know what they will do is to let them do it, to run the simulation, step by step, in real time. The weather is a classic example. Even with the most powerful supercomputers, we cannot predict the weather with perfect accuracy beyond a few days, because the system is so complex and sensitive to initial conditions that small errors in our model are rapidly amplified. The universe itself may be the ultimate, computationally irreducible system. If this is the case, then a complete, predictive knowledge of its future is not just practically, but fundamentally impossible. The universe's story can only be told by living it. This inherent unpredictability is not just a matter of complexity. It is also a matter of the fundamental, probabilistic nature of the quantum world. As we have seen, the universe, at its core, is not deterministic. It is governed by the laws of probability. We can never predict with certainty when a single radioactive atom will decay. We can only know the probability of it decaying in a given time interval. If the universe itself operates on this probabilistic logic, then how can we ever hope to map out a single, definite reality? We are not chasing a single, hidden answer. We are trying to understand a vast and constantly unfolding landscape of possibility. All of these limits the uncertainty of the quantum world, the incompleteness of mathematics, the emergence of complexity, the irreducibility of computation, the probabilistic nature of reality bring us to a final and deeply philosophical question. Are these barriers epistemic, meaning they are a result of our own human limitations of knowledge and perception, or are they ontic, meaning they are a fundamental built-in feature of reality itself? Some philosophers in the instrumentalist tradition would argue that they are epistemic. Science is just a tool for making predictions, and its inability to provide a complete, certain, and final picture of reality is not a failure, but a reflection of its proper limited scope. Others, in the realist tradition, would argue that they are ontic. Our scientific theories, in their very structure, are telling us something deep and true about the nature of reality, that it is, in its essence, incomplete, uncertain, and open-ended. The quest to decode reality, then, is not a quest to find a final, single answer. It is a journey into an ever-deepening mystery. It is a process that requires not just intellectual rigor, but also a profound sense of humility, of wonder, and of acceptance of our own, and perhaps the universe's own, fundamental limitations. The tapestry of reality is not a finished work of art to be admired from a distance. It is a living, breathing, and constantly evolving fabric, and we are not just its observers, but an integral part of its intricate and beautiful weave. The strange and beautiful world of quantum mechanics, with its principles of superposition, entanglement, and measurement, does not just challenge our understanding of the physical world. It also offers a new and profound lens through which to view the deepest mystery of all the nature of our own consciousness. The dialogue between quantum physics and the study of the mind has long been a fertile, if often speculative, ground for inquiry, a place where the most advanced theories of science meet the most ancient questions of philosophy. Could it be that the way we perceive, think, and experience the world is fundamentally tied to the bizarre and counterintuitive logic of the quantum realm? At the very heart of quantum mechanics lies the concept of measurement, the process by which the ghostly probabilistic world of quantum superposition collapses into the definite, singular reality of our classical experience. As we have seen, the role of the observer in this process is deeply enigmatic. While most physicists would argue that a conscious mind is not necessary for the collapse to occur, the very structure of the theory, with its inherent distinction between the unobserved system and the observing apparatus, seems to hint at a special role for information and awareness. This has led some thinkers to propose a more direct link between the quantum and the mental. Could our own subjective experience of a single, coherent reality be a macroscopic reflection of this fundamental process of wave function collapse? Could each moment of conscious awareness be a moment of quantum decision, a point where the vast superpositional potential of our brain's neural activity is resolved into a single, definite thought, feeling, or perception? This brings us to the fascinating idea of cognitive superposition. In our everyday waking lives, our minds often seem to entertain multiple and sometimes contradictory possibilities at once. In a moment of indecision, we can feel the pull of different choices. We can mentally simulate different potential futures. A classical computational model of the brain might see this as a simple, sequential process of weighing different options, but a quantum perspective offers a more radical possibility. Could the brain, at some level, be operating like a quantum computer, capable of holding these different possibilities in a genuine physical state of superposition? Could our subjective experience of indecision be the conscious correlate of an uncollapsed superpositional state in the quantum activity of our neurons? This is a bold and highly speculative idea, but it is one that is being taken seriously by some researchers at the frontiers of neuroscience and quantum biology. The search for a physical quantum basis for consciousness is not just a philosophical fancy. It is a field of active, if controversial, scientific research. We know that biological systems are not just classical, chemical machines. There is growing evidence that certain biological processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field, may be harnessing the strange and powerful effects of the quantum world. Could the human brain be another example of this quantum biology? The orchestrated objective reduction theory, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is the most well-known and specific model for how this might work. It posits that the fundamental units of quantum computation in the brain are not the neurons themselves, but the microtubules, the tiny cylindrical protein structures that form the cytoskeleton of our cells. Penrose and Hameroff argue that the quantum states within these microtubules can exist in a superposition of different configurations, and that these superpositions are the physical basis of our pre-conscious processing. Consciousness in this model arises at the moment of objective reduction, a spontaneous collapse of this quantum superposition that is triggered by a fundamental gravitational instability at the Planck scale. Each of these collapse events, happening many times a second, corresponds to a single, discrete moment of conscious experience. The Orch-OR theory is highly speculative and faces a number of significant scientific challenges, particularly the question of how a fragile quantum state could be maintained in the warm, wet, and noisy environment of the brain. But it is a testament to the growing interest in exploring the potential quantum nature of the mind. The observer effect in quantum mechanics, the idea that the act of observation can influence the state of a physical system, also finds a powerful metaphorical, and perhaps even literal, resonance in our understanding of consciousness. Our attention, our awareness, is not a passive spotlight that simply illuminates a pre-existing mental landscape. It is an active, creative force that shapes and transforms our inner world. When we bring a quality of mindful, non-judgmental awareness to a difficult emotion, like fear or anger, we can often feel its energetic quality shift and change. The act of observing it, without being identified with it, seems to collapse its power, to transform it from a solid, overwhelming reality into a more fluid and manageable experience. This is the basis of many contemplative and therapeutic practices. And it is an experience that hints at the possibility that our consciousness is not just a product of the brain, but is a fundamental, causal agent in the brain, a force that can influence the very physical processes that give rise to it. The bridge between the quantum and the classical, the strange and the familiar, may be found in the process of decoherence. As we have seen, decoherence is what explains why we do not experience the world as a constant, blurry superposition. A quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence. The information about its superposition is spread out into the surrounding world, and for all practical purposes, the system behaves classically. This principle is what safeguards our classical, everyday reality from the bizarre, underlying quantum weirdness. But it also offers a new way to think about the nature of perception itself. Our sensory organs, our eyes, our ears, our skin are macroscopic measuring devices. They are constantly interacting with and entangling with the quantum systems of the external world. The act of perception is a process of decoherence. When a photon from a distant star hits a retinal molecule in your eye, it triggers a cascade of classical chemical events. The quantum information of the photon's superpositional state is effectively measured and collapsed into a definite, classical signal that is then processed by your brain. Our classical perception of the world is, in this sense, a consequence of the constant entropic loss of quantum information. We see a definite, classical world because our very act of seeing is a process that destroys the underlying quantum reality. This leads to a profound and humbling conclusion. The reality we experience is not the full reality. It is a collapsed reality, a simplified and likely very partial representation of a much richer and far stranger quantum world. The discussion of consciousness and quantum mechanics inevitably leads to the age-old debate about free will. A classical, deterministic universe, governed by the clockwork laws of Newton, seems to leave no room for genuine freedom. Our choices would be nothing more than the inevitable outcome of a long chain of prior causes and effects. But the quantum world, with its inherent, irreducible randomness, seems to open a door. The collapse of the wave function is a probabilistic event. The outcome is not predetermined. Some have argued that this quantum indeterminacy could be the physical basis for our experience of free will. Perhaps our choices are not the result of a deterministic, computational process in our brains, but are, at some level, the result of the amplification of these random quantum events. This is a controversial idea, as it seems to equate free will with pure chance, which is not what we usually mean by freedom. But a more sophisticated version of this idea suggests that our conscious mind may be able to influence the probabilities of these quantum events, to steer the collapse of the wave function in a way that is consistent with our intentions, without violating the statistical laws of quantum mechanics. This is a deep and difficult problem, and one that is far from being solved. But the dialogue between quantum mechanics and consciousness, for all its speculative nature, is a powerful and important one. It is a dialogue that is pushing the boundaries of both science and philosophy. It is forcing us to question our most basic assumptions about the nature of reality, of the mind, and of the relationship between the two. It is a reminder that the universe is far more intricate, far more interconnected, and far more wondrous than our classical intuition can ever reveal. And it is an invitation to explore the deep and as yet uncharted territory where the mysteries of the outer cosmos meet the mysteries of our own inner world. The universe is brimming with information. It is encoded in the complex, swirling patterns of a galaxy, in the precise, orbital dance of a planetary system, in the fiery thermonuclear heart of a star, in the elegant double helix structure of a DNA molecule, and in the strange probabilistic wave function of a single subatomic particle. From the grandest cosmic scales to the most infinitesimal quantum ones, information is the thread that weaves the fabric of reality. But what happens to this information over the long and often violent course of cosmic history? Is it preserved forever, a perfect, indelible record of all that has ever been? Or can it be lost, erased, destroyed in the great entropic wash of time? This is one of the most fundamental and deeply debated questions in all of modern physics. A question that touches on the nature of time, of entropy, of black holes, and of the very laws of the universe itself. To understand the fate of information, we must first understand its foundations in both classical and quantum physics. In the classical world, information is, in principle, always preserved. This is a direct consequence of the deterministic nature of classical laws. If you know the precise state of a closed system at one moment in time, the position and velocity of every particle, then the laws of physics allow you to, in principle, calculate its state at any other time, both in the future and in the past. Information is never lost. It is just rearranged. But the quantum world, as we have seen, operates on a different logic. The process of decoherence seems to imply a fundamental loss of information. When a quantum system interacts with its environment, the information about its delicate superpositional state is rapidly spread out and dissipated, becoming, for all practical purposes, irretrievably lost. This is why our macroscopic world appears to be classical, even though it is built from quantum components. The quantum weirdness is constantly being washed away by the entropic tide of environmental interaction. Understanding and controlling this process of decoherence is one of the central challenges in the development of practical quantum technologies. To build a powerful quantum computer, we must find ways to isolate our qubits from their environment, to shield them from the relentless process of decoherence, long enough for them to perform their complex calculations. The quest to build a quantum computer is, in a very real sense, a battle against the informational entropy of the universe. The deep and intimate connection between information and entropy is a cornerstone of modern physics, a connection that is most beautifully illustrated by the laws of thermodynamics. The second law of thermodynamics, as we have seen, states that the entropy, or disorder, of a closed system always increases over time. This is the law that gives time its arrow. But information can be seen as the very opposite of entropy. It is a measure of order, of structure, of reduced uncertainty. When we gain information about a system, we are, in a sense, locally reducing its entropy. This is the paradox of Maxwell's demon, the hypothetical being who could seemingly violate the second law by sorting hot and cold molecules. The resolution to the paradox lies in the realization that the demon itself, in the process of acquiring and processing information, must generate at least as much entropy as it reduces, thus preserving the overall validity of the second law. This connection was made even more explicit by Landauer's principle, which states that the erasure of information is an irreversible, entropy-increasing process. To erase a single bit of information from a computer's memory, you must release a minimum amount of heat into the environment. Information is not an abstract, disembodied entity. It has a real physical cost. It is tied, by the fundamental laws of nature, to the world of energy and entropy. On the grand cosmic scale, the universe itself can be seen as a vast and ancient repository of information. The cosmic microwave background, the faint afterglow of the Big Bang, is not just a uniform glow. Its tiny temperature fluctuations are a snapshot of the primordial information, the quantum seeds from which all the structure in the universe grew, the large-scale distribution of galaxies, the intricate chemical composition of the stars, the complex geological history of a planet. All of these are records. Archives of the universe's long and complex evolutionary story. But what is the ultimate fate of all this cosmic information? Does the universe have a finite memory? The accelerating expansion of the cosmos, driven by dark energy, raises a profound and unsettling possibility. If the universe continues to expand at an ever-increasing rate, then the information contained in distant galaxies will eventually be stretched and redshifted into oblivion, lost forever beyond our cosmic event horizon. The observable universe will become an increasingly barren and information-poor place. And the enigmas of dark matter and dark energy add another layer of mystery. Does dark matter, which makes up the vast majority of the matter in the universe, play a role in storing or processing information? Or is it an informationally inert, passive background? And what is the informational nature of dark energy itself? Is it a simple, constant energy of the vacuum, or is it a dynamic, information-rich field that is evolving over time? These are some of the most profound and challenging questions in all of cosmology. Perhaps the most intriguing and challenging intersection between information and the cosmos lies in the nature of gravity itself. For decades, the quest to unify general relativity and quantum mechanics has been the holy grail of theoretical physics, and in recent years, a new and powerful idea has emerged that gravity itself may not be a fundamental force, but an emergent phenomenon, something that arises from the deeper quantum informational structure of the universe. The idea is that the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space. The curvature that we perceive as gravity is a macroscopic manifestation of the intricate web of quantum correlations between the fundamental constituents of reality. In this view, information is not just in the universe. The universe is information. This is a radical and beautiful vision, and it is one that is supported by the holographic principle. The idea that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This principle, which first arose from the study of the thermodynamics of black holes, suggests that our familiar three-dimensional world may be a kind of cosmic hologram, a projection of a more fundamental, two-dimensional informational reality. This would have profound implications for the black hole information paradox. If the information about the matter that falls into a black hole is encoded on its two-dimensional event horizon, then it is never truly lost to the universe. As the black hole evaporates, this information could be subtly and complexly imprinted onto the outgoing Hawking radiation, thus preserving the fundamental principles of quantum mechanics. And what of the ultimate fate of the universe in this informational picture? If the universe is destined for a heat death, a state of maximum entropy where all energy is evenly distributed and no useful work can be done, would this also be a state of information death? Would all the complex ordered information that has been created over billions of years of cosmic and biological evolution be lost in a final, uniform sea of thermal noise, or could information persist? Even in this seemingly final state, some speculative theories suggest that even in a heat death scenario, the quantum fluctuations of the vacuum would continue, and that over immense, almost unimaginable timescales, new, ordered structures could spontaneously fluctuate into existence. The universe could, in a sense, be reborn from its own informational ashes. The study of information in physics is a rapidly evolving and incredibly exciting field. It is a field that is blurring the lines between physics, computer science, and philosophy. It is forcing us to rethink our most basic concepts of reality, of space, of time, of causality. And it is a field that is driven by a single, powerful, and unifying idea that to understand the universe, we must understand its information. The cosmos is not just a collection of matter and energy. It is a story, a message, a vast and ongoing computation. And in learning to read this cosmic code, we are not just deciphering the secrets of the universe. We are also, in a very real sense, discovering the deep informational nature of ourselves. The future of humanity has always been inextricably linked to our ability to create, to process, and to transmit information. From the invention of language and writing to the development of the printing press and the internet, every major leap in our information technology has been a major leap in our civilization. And today, we stand on the cusp of a new and potentially even more transformative revolution. A revolution that is being driven by the strange and powerful logic of the quantum world. The future of information is a story of two converging technologies, artificial intelligence and the quantum internet. And their combination holds the promise to redefine not just our technology, but the very fabric of human existence. Artificial intelligence, once the stuff of science fiction, is now a ubiquitous part of our everyday lives. It is in the virtual assistants that organize our schedules, in the recommendation algorithms that shape our cultural tastes, in the sophisticated systems that help doctors to diagnose disease and scientists to analyze vast and complex data sets. The power of modern AI lies in its ability to learn from data, to recognize patterns, and to make predictions with a speed and an accuracy that can far surpass human capabilities. But for all its power, our current AI is still limited. It is a form of narrow AI, a system that is incredibly good at performing specific, well-defined tasks, but that lacks the general, flexible, and creative intelligence of a human mind. The story of AI is still in its early chapters, and the next, and perhaps most exciting, chapter may be written in the language of quantum information. The concept of quantum information, as we have seen, is a radical departure from the classical binary logic of our current computers. A quantum computer, by harnessing the principles of superposition and entanglement, can process information in a fundamentally new and more powerful way. It can explore a vast, multidimensional computational space simultaneously, giving it the potential to solve certain classes of problems that are, for all practical purposes, unsolvable for any classical machine. Imagine an AI system that is not limited by the linear, step-by-step logic of a classical computer, but can think in the rich, probabilistic, and superpositional language of the quantum world. This is the promise of quantum AI. Why? A quantum AI could, in principle, analyze a vast and complex landscape of possibilities in an instant, allowing it to solve complex optimization problems, to design new materials with novel properties, or to discover new drugs by simulating the quantum behavior of molecules with perfect fidelity. It could be an engine of scientific discovery and technological innovation of unprecedented power. But the quantum revolution is not just about computation, it is also about communication. And this is where the second part of our story begins, the development of the quantum internet. A classical internet transmits information as bits of data encoded in pulses of light or electrical signals. A quantum internet would transmit information as qubits encoded in the quantum states of single particles, like photons, and its primary, and most revolutionary feature would be its inherent and perfect security. As we have seen, the principles of quantum mechanics, like the no-cloning theorem and the observer effect, make it impossible to intercept or copy a quantum communication without being detected. A quantum internet would be a truly unhackable network, a development that could revolutionize every industry that relies on the secure transmission of data, from finance and government to healthcare and defense. But the potential of a quantum internet extends far beyond secure communication. It would also be a network that can transmit entanglement. It would allow us to create and distribute these strange, non-local quantum connections between distant quantum computers, linking them together into a single, global quantum computational network. This would allow us to tackle problems that are too large and complex for even a single, powerful quantum computer. It would be a new kind of global collaboration, a new way of harnessing the collective, computational power of the quantum world. Now, let us think even bigger, even more speculatively. What is the ultimate, long-term potential of this quantum information revolution? The astrophysicist Nikolai Kardashev famously proposed a scale for categorizing hypothetical and advanced extraterrestrial civilizations based on their ability to harness energy. A Type 1 civilization is one that can harness all the energy of its home planet. A Type 2 can harness all the energy of its host star, and a Type 3 can command the power of its entire galaxy. We can imagine a similar scale for the mastery of information. What if a future advanced civilization could learn to harness and process information on a cosmic scale? What if they could build a galactic-scale quantum internet, a network that connects not just computers, but planets, stars, and perhaps even different regions of space-time? This is a provocative and highly speculative notion, but it is a logical, long-term extension of the technological trajectory we are on. If information is the currency of intelligence, then the ability to manage information on a cosmic scale could allow a civilization to unlock secrets of the universe that we can't even begin to comprehend. Could this be an evolutionary milestone for advanced life? Could the mastery of quantum information be the key to reaching a new and higher level of cosmic consciousness? Naturally, these bold and futuristic ideas spark a host of profound ethical and philosophical questions. The development of a true general artificial intelligence, whether classical or quantum, would be a watershed moment in the history of life on Earth. How would we ensure that such an intelligence is aligned with human values? How would we prevent it from being misused? What would be our own role and purpose in a world where we are no longer the most intelligent beings on the planet? These are not just technical challenges, they are deep, societal, and existential ones. Similarly, the development of a global quantum internet, while offering the promise of perfect security, also raises questions about privacy, surveillance, and control. Who would own and control this new fundamental layer of our information infrastructure? How would we ensure that its benefits are distributed equitably and that it does not become a tool for creating an even wider gap between the haves and the have-nots of the information age? The democratization of these powerful new technologies will be one of the most critical challenges of the coming century. And of course, there are the skeptics. Some argue that the warm, wet, and noisy environment of a biological brain is simply not conducive to the kind of delicate, coherent quantum processes that would be needed for a quantum mind. Others argue that even a powerful quantum AI would never be able to replicate the true, subjective experience of human consciousness, with all its intuition, its creativity, its capacity for love and sorrow. These are valid and important critiques, and the debate is far from settled. But even if the most ambitious claims for quantum consciousness and AGI do not come to pass, the journey itself is transforming our world. The promise of quantum information is reshaping our understanding of artificial intelligence. The development of the quantum internet is redefining the future of communication. And the futuristic vision of a civilization that can harness information on a cosmic scale is providing a new and powerful lens through which to view our own long-term evolutionary future. The future of information is not just about faster computers or more secure networks. It is about redefining what it means to live in an interconnected, intelligent, and information-rich world. It is about uncovering new truths, not just about the universe, but about ourselves. It is about understanding what a civilization can achieve when its technological innovation is guided by its deepest imaginative and ethical aspirations. As we conclude this exploration, the question we are left with is not, what is the future of information? But rather, how will we choose to shape our future with the new and powerful forms of information that we are now, for the first time in history, beginning to create? The possibilities are infinite, the questions are profound, and the answers, for now, are waiting for us in the strange, beautiful, and endlessly creative quantum unknown.